Is this really happening, the EMEA Livestream for Citus Con 2023?
Yeah, it is. I'm very excited.
I did a last-minute camera upgrade during the waiting room. I'm wondering what our producer is going to say. Do I look okay? Is it working?
It looks. I think it looks fine.
Okay. Well, my name is Claire Giordano. Welcome to Citus Con 2023. My co-host today is
Jelte Venema. I did a talk yesterday at the Americas Livestream.
And now you're here for the whole EMEA live stream to kind of shepherd us through all these great talks. We've got some logistics to cover with you in a second, but the first thing I want to say is thank you to all of you who are joining us today. One of the things we're trying to do with this conference is just share more knowledge and expertise about Postgres and about Citus. Postgres is growing like crazy, and it's partly because of all the work and energy that the developers put into it, but also that the users put into it, sharing their tools, creating new tools, sharing their expertise. So we're happy to be part of that whole knowledge sharing fest as well. Should we do logistics?
Sounds good to me.
Okay. Awesome. So obviously this is the EMEA live stream. If you meant to be at KubeCon or one of those other conferences, you got to flip over to somewhere else. There are 37 talks in CitusCon. So there's the 6 talks today. There were 6 talks yesterday in the Americas live stream. And we'll pop some links on later with where you could find the replays of the Americas live stream. And then there are 25 on-demand talks that dropped yesterday.
That sounds like a lot of talks, Claire.
I know. So I wrote a blog post called The Ultimate Guide to CitusCon, where I categorized the different talks into different buckets so that you could figure out, based on whatever it is you do with Postgres, which ones are most relevant to your job and your work, or that whatever you're curious about. So there's a URL on screen for that one too. I think we want to...
we want to thank the speakers as well, because I mean those are the people that make the whole conference possible. Without them, there wouldn't be one. So thanks all of you, including myself, of course.
Thanking yourself. Well, if you've ever given a conference talk, you know it's a lot of work and a lot of practice, feedback. There's what you say, there's how you present yourself, there's your slides. And so, yeah, we really, really appreciate everything that all of these experts have done to pull off these talks. There is a code of conduct. There's a link on the right-hand side of the slide that's showing to where you can find the full code of conduct online or report an issue. And the code of conduct is what you might expect, right? To be respectful and inclusive, friendly, welcoming, be kind to each other, basically. And this matters for virtual events as much as it does for in-person. Accessibility, captions. I like captions. I think they're like the ultimate curb cut effect. I put them on all the time, even when the talk is in English and I speak English. So there's live captions available on YouTube for the live stream today. And then all those on-demand talks that were published, our team QA'd all of those captions. So you should see Postgres spelled correctly. And they're available in 14 languages total as well. So go ahead and take your pick. Discord.
There's a Discord channel. It's really nice. Yesterday I gave a talk, and afterwards there were lots of questions and discussion about the talk. So today let's do the same. It's sort of our virtual hallway trick. I mean, most conferences, part of it is going to the talk, but part of it is also connecting with the people that are also going to the talk. So this is kind of the place where we want to do that. And yesterday I think it worked out very well. So let's make it great again today.
It's fun. It's fun. So the URL is showing on the screen, aka.ms/open-source-discord. And then when you get there, you go into the hashtag CitusCon channel. So please join us, give feedback, you don't have to ask questions. You can just drop emoji or tell someone, maybe thank someone if you particularly liked or benefited from their talk. So this is what we're going to see today. We don't want to walk through this now because you're going to get to hear from the speakers themselves. But these are the 6 talks. And then just a reminder that there were 6 talks in the Americas live stream yesterday. That's the correct playlist to get to see that live stream on replay right now. We will be cutting the whole live stream into 6 individual pieces and publishing those in the next couple of weeks as individual talks on YouTube and on the Microsoft portal. But if you want to watch it later today, it's available. Just hop on over there.
And there's also 25 on-demand talks, like Claire already said. That's a lot of talks. They don't even fit on one slide. So
yeah, there's 2 slides here.
So depending on what you're interested in, take a look. They're really good.
This takes you to the Citus Con schedule page, and you might have to reload the page. It's the on-demand tab should be open, but when you reload it, you'll see those YouTube embeds are there for all 25 of those talks. So yeah, and then if you're promoting on social, use hashtag CitusCon so other people can share and see, and will notice your posts. And oh yeah, the swag. So check this out. Maybe Dwight, put me up larger for just a second. There's an activity book that's kind of super cool that is all about Postgres. That's kind of fun, and lots of stickers. And then there's a cool pair of socks in the swag bag too. If we pop back,
and those are so exclusive that even you don't have them, right, Claire?
Yeah, I don't have the socks. There's a picture of Teresa, who's the co-chair for the event, that's on Twitter right now. I think I popped it into the Discord as well. And she's holding them. So we know they exist, but I do not own a pair yet. So this swag bag, the URL is showing on the screen. You can enter to win, and the code will be shared in the banner in every talk today. So you can grab it at any point along the way. And then there's also even more sticker packs that are available with a slightly different code. So you can enter for both, enter for the swag bag and the sticker pack. We know last year we didn't have swag. Well, the speakers got cool gifts, but that was it. And we got feedback that said, hey, is there a sticker? Is there some way that I can get something? So that's why it's here this year.
Do you usually have stickers on your laptop, Claire?
I have a ton of stickers on my laptop.
Are there Citus Con stickers already on there?
There's the Citus open source Elite Corn. And oh yeah, last year's Citus Con is on there too.
But and the new one, not yet.
The Postgres Elephant. The new one, not yet. But I do have the new one. It's right here. I should just put it on. It's kind of cool. Right. Yeah, I've had people stop me on trains, stop me in airports, and stop me in coffee shops when they see some of these stickers, and it just starts a whole conversation. Like, what? Do you use Citus? Are you a database person? And so that's always kind of fun when that happens. Cool. Okay, we need to get to the keynote speaker here. So I do want to make sure everybody sees this QR code. There is a survey. The survey is, the first page is about the event, and the subsequent pages are about the talks. And you can fill out the survey multiple times. So like if you watch a few talks today, the speakers would love your feedback. And so you can go in and do that, even if you plan to watch some of the Americas replay later or the on-demand talks later. And the survey is open until next Friday, the 28th. So there's also a short URL on the screen. So yeah, we mentioned Discord already.
Yeah, right? It's so important that we mention it again. Just go there. Connect with the other people. That's how we make everything. How we make it feel nice.
I think it's time, drum roll, to introduce our keynote speaker, Marco Slot. So, awesome.
Hey everyone.
Hi Marco.
Hey Marco. Nice to see you.
Good to see you too. Excited to be here. It was a great session last night, so I'm really looking forward to today as well.
I think today's speakers, including you, can definitely follow it up with a good.
I'll try.
session.
So for those of you who don't know Marco Slot, he is the lead architect on the Citus open source database project at Microsoft. He started working at Microsoft over 4 years ago as part of the Citus data acquisition. So he actually was working on Citus and Postgres from, I don't know. Well, you're going to probably cover that in your talk, your whole background. So I don't want to steal your thunder, but I just wanted to explain your expertise. And then I think we should just let you take it away. You've got your PhD in distributed systems from Trinity College Dublin. So I think you know what you're talking about, and let's just dive in.
All right. Sounds good. All right. Yeah, I've actually been working on Citus and distributed Postgres for 9 years now, which shockingly I recently realized is 25% of my life. But it's actually because it's still such an interesting problem. Like and what I want to do today is kind of talk you through some of the core underlying challenges of distributed Postgres and some of the things we've done in Citus to try to solve them. Look, when we put up my slides, thanks. So you're probably familiar with Citus as a project because it's the namesake of this conference, but basically it's a distributed Postgres implementation that's built as an extension on top of Postgres. So it gives you the ability to distribute and replicate Postgres tables across a cluster of PostgreSQL servers. And then you can connect to any of the nodes and you'll see that same set of tables. Under the covers, they will be sharded across all the nodes. So you can, and queries that you do on the distributed tables will be routed or parallelized across the cluster. And it's open source. You can get it from GitHub. There's packages, Docker images, source code, whatever, however you want to consume it. And you can also get a managed cluster using the Azure Cosmos DB for Postgres service. Now, why is something like Citus needed? Why do we want distributed Postgres? Well, it's pretty simple. So Postgres is great. It's robust, it's versatile, it's efficient, it's extensible. People love it. It gets used more and more. It's still one of the fastest growing databases, but sometimes it gets used a little bit too much, and then you run into various scalability problems. And you kind of always have to sort of think in terms of the realities of today, the hardware realities of today. Nowadays, most software, including databases, is deployed to cloud hardware, meaning virtual machines in data centers. And virtual machines are very convenient. You can get as many as you want, whenever you want, for as long as you want. But they are typically capped at a certain size, let's say 64 cores, if not virtual cores, then physical cores, maybe half a terabyte or a terabyte of memory. And that's about it, because it's just not economical to have much larger virtual machines than that. And then the storage is nearly always a network attached disk that's replicated over the network. And that's nice in terms of availability and durability and resizing and snapshots and encryption. But the downside is that it incurs some latency and it limits your storage bandwidth in terms of IOPS. And then there's the software realities that nowadays a lot of transactional applications, like in the past, you may have had transactional applications that were tied to something going on in the physical world, like a hospital administration or an airline booking system. But there's only so many planes, only so many patients. But nowadays, you can have these applications that are almost like unbounded in terms of their growth, at least as long as there's more people in the world, such as software as a service applications that can quickly grow in the number of tenants, or IoT applications that can have more and more devices, sending more and more observations, social applications with more and more interactions. So this kind of data intensity from these applications can overwhelm Postgres on typical modern hardware. And what that looks like is, for example, if your traffic grows, you get more and more CPU usage, you use more of your storage bandwidth. If a greater section of your data is frequently read, so it's like your working set, then what happens is more data will have to be read directly from disk rather than from cache, and that means you use more of that limited storage bandwidth, and your data grows. Now, data grows, often you can think of it, okay, I just need a bigger disk, but what happens in a lot of Postgres workloads is that they're not very trivial. There's a mixture of operations, and maybe there's a very small number of kind of batch operations or analytical queries. And as your data grows from, let's say, a gigabyte to 10 terabytes, those operations start taking so much more resources that it kind of starts dominating your whole workload. So that's also a very common scalability problem that you have to factor in. And then there's Postgres specific problems that have to do a little bit more with the implementation of Postgres. That there's one write ahead log all the sessions try to kind of get their bytes into, and it's a bit sensitive to storage latency, especially when the storage device is saturated. You get, well, maybe not excessive, but you get quite a lot of memory usage due to the process-based architecture. If there's a lot of update and deletes, you can get table bloat. There's going to be a great talk about that later as well. And in essence, the promise of distributed Postgres is that you get to run away from these problems by scaling out. So as these applications grow along some multiplier, you can add more capacity such that you don't quite hit those scalability issues on any individual node, and you don't have to deal with them, and your customers don't feel the pain of things getting very slow. But no one has come in and just submitted a patch to Postgres and say, oh, let's make it distributed. So why is this such a hard problem? And this is a tricky, complex question which doesn't have like one easy answer. So there's many different facets, and I'll only discuss a few. But I want to discuss some of the problems that to me are very core to building a distributed Postgres database, and they're not often always talked about. One is the data locality problem. And to me, this is the combination of having network latency between our machines in this cloud data center, where the cloud maybe tries to put our machines close together, but there's not always capacity. So we end up with a few hundred microseconds up to a millisecond of latency in between the machines, which wouldn't be so bad. But we also have in Postgres workloads relationships. Relational databases are very much relational. The rows are joined together, they are grouped together, they're in a transaction together, they're in foreign key relationships, and then also transactions depend on each other, like queries depend on updates to the same row, inserts match the where clause of an update or not. So there's all these kind of explicit and implicit relationships in the data model, in the workload. And for the database to deal with those relationships, to evaluate them, it needs to know both sides of the relationship effectively. So basically, the CPU needs to kind of pull both sides into itself and then do some computation. And so this could look like we're doing a join between one set of rows and rows in one table and another table. So we're walking through rows on one side, and for every row on the left, we need to do like an index walk to find the row on the right. And every index page requires memory access, sometimes disk access. So it adds a little bit of time. Memory is very fast, like 100 nanoseconds or microseconds. Disk can be a lot slower because of the network, but overall, this is still a pretty quick operation. Now, what happens if we take our relational data model and we try to spread it across machines? Everything gets extremely slow. And so this is, in some sense, a part of the essence of the distributed Postgres problem, that the baseline is for everything to get slow when you spread it across multiple machines. Because now, let's say your index is laid out over the network, your CPU has to fetch every index page. It takes a millisecond. And so maybe the whole operation joining two rows takes like 10 milliseconds, and then the whole query takes 100 milliseconds. Now, it's not necessarily bad for things to take a little bit longer. You can still scale even if things take a little bit longer. But the problem is we're dealing with Postgres, and the Postgres protocol is synchronous and interactive. I send a query and then I wait for the response, and then I send the next query. I don't tell the database like what my whole transaction is going to be. And what that means is that the maximum throughput you can get on a single connection is essentially 1 over the response time, and the total throughput is the number of connections divided by the response time, no matter how much hardware you have. Normally, your expectation is that, okay, my machine is overloaded, my response time goes up, and that's why I'm seeing lower throughput. But in the case of a distributed database, actually response times might go up just by adding more hardware. So your throughput might go down. And then the other problem is that many client libraries, such as object relational mappers, they're not very efficient. They don't expect to have high latency, so they send long transaction block, set some settings, send some save points, then do the same query several times for no reason. And so very quickly, your 10 millisecond query becomes a 100 millisecond transaction, or a 100 millisecond query becomes a 1 second transaction. And then if you have 1 second transactions and you still want to get super high throughput, let's say 1 million transactions per second, you need 1 million connections. And that's really not very practical from the application point of view, even if your database was able to handle it. So to actually get good scalability characteristics for a distributed Postgres database, we need most of the operations to be not distributed, like to be local to a particular machine. And then one of the nice things about having a distributed database, for example, is that we can ensure that there's always enough memory to keep our working set in memory, and therefore can avoid disk access. So it can actually be much faster, and we have the capacity to scale to any size. And to do this, you basically want that there aren't too many relationships across the different machines in your cluster. And that implies that you have certain workload patterns and certain ways of modeling your data. And so the way we've addressed this problem in Citus is by giving you two very important primitives. They're not groundbreaking or unique to Citus, but they are nonetheless extremely important. And first is co-location. So you can distribute two tables by a common dimension, such as device ID in an IoT app, and then co-locate by that and co-locate them together. And that way, the same set of devices across these different tables will always be on the same node. And therefore, joins on the device ID, foreign keys, and other relationships along that dimension can all be evaluated locally on that node. Similarly, you can create reference tables, which are replicated everywhere, and then joins and foreign keys and other operations on any column with the reference table will be local to each node as well. And then the Citus Query Planner, if it sees that a query just can be fully handled by one node because of the way data is organized, it can just take that query and forward it essentially to that node. And one of the nice things there is because we're building this on top of Postgres is very good at just dealing with answering a query on a set of local tables. It can, use its indexes, it can use statistics, it can use its query optimizer. So we don't lose any of the efficiency we had compared to Postgres. This also works for inserts and updates and stored procedures and other operations. And also, even if a query doesn't go to a specific node, if we're joining on the shard key or joining with reference tables, we can still delegate the entire join and complex subqueries to each node and parallelize and then aggregate the results. If you have non-collocated joins, performance inevitably is going to be worse because then you do have to make, then Citus does have to make all the network round trips. But this gives you the opportunity to model your data in such a way that it's you essentially avoid the distributed Postgres problem, the data locality problem. And what this means in practice is that, and these are some benchmarks that GigaOM released comparing different distributed Postgres implementations. And for reference, I added a HammerDB result from a very large Postgres server. And in the Citus case, in the Cosmos DB case, because we take kind of data locality into account, because we lean on the efficiency of Postgres, we can be much faster than Postgres. But if you don't, you might be much slower than Postgres. So this is really the difference between having performance at scale or just being distributed. So it's, again, one of the most important distributed Postgres problems. But it does also imply that you now have a new problem, which is the distributed data modeling problem. So you have to find a way to map your workloads into these distributed data modeling primitives. And a common technique is just essentially do what the NoSQL databases do, is you distribute tables by primary key. And that's still quite good for microservices, for example, that just use a single table, maybe with a JSON column, and that can scale well for high throughput CRUD workloads. But if you have a more complex application, let's say a software as a service application with different dimension, a to-do list, context, emails, labels, filters, you kind of have a lot of tables. But typically, the application is always doing a query in the context of a single tenant. So what you can do is then distribute and collocate those tables by the tenant ID and kind of get the nice scalability characteristics. And in IoT applications, it's often nice to distribute by the device ID and parallelize the queries. Another example, and there's different examples. Another example is geospatial apps often have some kind of map data structure that they can then make a reference table, and this is a table that contains like polygons of like this is the shape of the Netherlands, and this is the shape of Germany, and then your point data, your observations, your traces can be a distributed table, and then you can join that with the map, and that will be a local operation on each node. So effectively, distributed Postgres works well for a set of workload patterns. And the ones we most often talk about for Citus are multi-tenant OLTP, high throughput CRUD workloads, and real-time analytics, dashboards with IoT and time series data. And these, even if you have a CRUD workload, you can still have SQL query and distributed transactions, but the essence of your workload should probably fit some one of these patterns. Though one nice thing, because Citus is an extension to Postgres, we don't change how Postgres work. If you don't distribute your tables, it does nothing, which means you can actually still have just regular Postgres tables and just distribute some of your tables and make some tables reference tables. That way you can have this hybrid between a regular Postgres database and a distributed Postgres database, and handle much more complex data models where your like dense relationships are kind of compacted into a single node, but then some very large table is spread across multiple nodes. So another problem that just won't go away is the versatility problem. The Postgres manual is huge. There's just so many features, different types of indexes and planning features and table spaces and full text search and geospatial. Like there's really an endless list of features. And the way to deal with this is, for a distributed database builder, is to just go at them one at a time, make distributed implementations one at a time, and where possible, find opportunities to take advantage of being a distributed database. For example, insert select command in Citus are really fast. Like if you insert into a distributed table, select from another distributed table, there's all sorts of ways in which that can be parallelized, even if it's not a collocated operation. So those are then things you can take advantage of if you have a large Citus cluster. And there's also still lots of gaps. We're working on things like schema level sharding. There's still gaps around snapshot isolation and geo-partitioning. And these are things we'll hope to resolve in the future, but it just takes a very long time to build a distributed Postgres database. And finally, and this one is a bit more controversial, but I've noticed over time that distributed databases exist at the intersection of two very different engineering disciplines, distributed systems and databases. And they have different focus areas and different things they care about most. And me as a distributed systems engineer, I'm very focused on trade-offs and like how within the constraints set by things like network latency, can I still provide something useful for a particular workload? Should I sacrifice some functionality to get there, or some other workload's performance to get there? Whereas database engineers tend to focus on much more generic solution and focus on just CPU efficiency and storage efficiency and correctness. And of course, both of these things are extremely important. Not one is not more important to the other when you're building a distributed database. They're just sometimes a little bit hard to combine. But what we found is that with being an extension, the core database engineering is effectively encapsulated in the Postgres project, and Microsoft contributes a lot to the project. I think now we're we're the fourth biggest contributor. And then Citus kind of wraps around that as an extension and is more focused on the distributed system side and making trade-offs that favor particular workloads that we see among Microsoft customers. So we found this to be a nice way to kind of keep the efficiency and the progress of the Postgres project, but while also building an advanced distributed database. So thank you very much for listening. So some of the key takeaways are distributed Postgres helps you run away from scalability problems, but latency can absolutely devastate performance. So your data modeling, whether you choose to model the data in a certain way or the database chooses it, it matters a lot. And that means some workloads will work better than others. And you should expect that some Postgres functionality is not available when you distribute your tables or use a distributed Postgres version. But I mean, these will all get better over time in all the implementations. So next steps, enjoy the live stream. I'll be on the hallway track all day on Discord in the next few days. And there's also some great on-demand talks, some on also like some of the scalability issues of Postgres I mentioned. If you want to start using Citus, I recommend checking our GitHub page, and there's also links to like the docs and other resources that can help you get started. All right, thanks very much.
That was wonderful, Marco.
Thank you, Marco. It was a great talk. I know a lot about Citus myself, but still I learned a few things.
Great.
Well, that's good to know. I want to make sure you don't know everything yet, Jelte.
Well, I'd like him to know everything.
So we have a few questions. The first is, what's the most unexpected use case of Citus that you've seen over the years? And yeah, I stole that question from you, Jelte.
Yeah, that's a nice question. So I think one of my favorites is the UK coronavirus dashboard, because I mean it was, apart from being like a very important public service, I think it was a great insight into the challenge of dealing with data, where it basically combines data from all these different sources at different granularities, different age, and different formats sometimes. And then it was a very small team, mostly led by Purya, who built this. And actually, a lot of the data integration just happens with like SQL queries that are parallelized using Citus, and then kind of rendered in the dashboard, and the results are cached in the dashboard. But yeah, I think that was great to see, and I'm still like, I sometimes think of the queries that Purya wrote, and that actually they just work beautifully in parallel, and they merge all of these different data sources, and in the end, it's something that everyone can go in and have a look at, and especially when Corona was a bit more active, or maybe it will be again in the future, hopefully not. But it was also a massively important thing. So that was a surprising to see, like just the pains of dealing with data, or the challenges of dealing with data. But it was very nice to work with the team there.
Well, that particular use case, Purya, that particular customer, UK HSA, I got so lucky that I was invited to co-author a blog post with Purya. So we did this massive deep dive, and I learned a ton in working on that with him. And in fact, we'll drop that link in the Discord for anybody who's interested, because Purya went into great detail about everything. And the thing I liked about it too is that he really embraced open source in that whole project. So one of the reasons he chose Citus and Postgres as the underlying database is because it was open source. He open sourced all of his queries. He open sourced the whole software stack. Like it's a very open solution. Yeah, and it was running on Azure too, I think, as a platform, because he didn't want to have to self-manage it.
Right.
Jelte, you had more questions.
Yes, I definitely had. So one is, you're mentioning like this network latency. It's a big part of the problem. Basically, it's sort of the core problem that everything else follows from. So wouldn't faster networks solve this problem in a sort of a completely different way?
Yes, it would, but within, like, let's say the hardware realities, that's actually a little bit challenging. So, I mean, in theory, cloud providers could give you this kind of gold-plated, hey, here's your rack, and machines are right next to each other with these extremely fast network links between them. But then you quickly get the question of like, well, what if I want to scale that out? What does my cloud provider do? Do they go and like move things around in the data center to just like put stuff next to each other again? Essentially, it's like not a cloud model anymore.
Like physically carrying your racks around.
yeah, basically. And then what kind of downtime that occurs. Also, if I have like this special rack where all the machines are next to each other, like what if that goes down? Like how's the availability handled? So let's say in a hypothetical timeline where cloud wasn't the main platform where we deploy our software, you'd probably end up with very different distributed database architectures. But I think even with features like placement groups and proximity placement groups, it's still not very economical, let's say, for the cloud to just you buy one machine, but it actually has to reserve the whole rack in case you want to scale out in the future with low latency. It's just not very practical. So that's a challenge, but definitely as hardware will evolve and some of the cloud techniques will evolve, distributed databases will have to kind of evolve with it as well.
Okay, and then sort of the final question, I guess, is I mean, you told a lot of things about what Citus does now, but what are you working on that, like, what's the next big thing for Citus, pretty much?
Is that rhetorical? I mean, you know the answer, right, Jelte?
I mean, I'm always interested in finding out what Marco thinks.
Okay, I'm in that camp too. So yeah, let's go.
Right. Yeah, I mean, I also have these different arcs in mind of like how long do we have, but I think in the short-ish term, one of the things we're very much focused on is make things easier for software as a service applications. So one of the things we're building is this schema level sharding, so that you don't have to specify a shard key, but every schema just goes into a different node, which makes it very easy to build these types of multi-tenant software as a service applications, because you don't have to specify a distribution key or anything like that.
Okay, that would be a big deal.
Yeah, I think so.
That sounds very interesting. Are there any downsides to doing that?
Yeah, I mean, you get more shards, let's say, more tables, which I mean doesn't have. I mean, it creates a downside on us that we then have to do more work to make Citus work well with a lot of tables. I think. I mean, there's some practical things like, okay, well, as a user, then I have to manage things across schemas rather than in one set of tables, like if I want to add a column. So, but I mean, this is actually a very common pattern that people already do on just regular single node Postgres with various ORMs. So we think it will work pretty well. A longer term, I think we need to get like completely flesh out the Postgres compatibility of distributed tables, so that just any query works and as efficiently as possible. Like there's like some of these really long arcs because we can make things faster and faster and faster. Yeah, there's various other areas we can get into, but like we probably also have to
move on to our next speaker, probably.
Yes.
Marco, big thank you for coming and giving this keynote today and being part of Citus Con and leading the project.
Yes, thanks a lot, Marco.
You're welcome, and thanks for having me.
All right, you're going to the Discord. He's going to the Discord. I'm sure he is. All right, so without further ado, I think we should welcome Thomas Monroe to the stage. Thomas.
Hi.
Hi, Thomas.
Hey, guys.
How are you?
Good. So, thanks
I know
for
you're joining from New Zealand. It's nighttime for you. I really appreciate.
Nighttime is out the window.
Yeah, nighttime is out the window. You gave a talk at Citus Con last year, on queues in Postgres, completely different topic. You are a Postgres hacker and committer, and you work at Microsoft. And your talk last year about queues in Postgres, and I know there's lots of controversy. Should you use Postgres for queues? No, I think you shouldn't. No, yes, I think you should. But it was one of the most popular talks in terms of like overall number of views. So I'm not putting any pressure on you today.
I see that topic's been raging on the internet in the past few days. I noticed someone wrote an article somewhere.
I saw some posts as well. Yeah,
it just keeps coming back. So you're going to be talking to us today, not about distributed Postgres, but about parallelism, right?
Yeah. So
Okay.
pretty much the opposite.
And
end
don't
of the
tell us
spectrum.
now, because we're going to leave the stage, and then you can dive in on what you're talking about. But Jelte, were we supposed to say anything else to make Thomas feel properly welcomed?
I think you did a great job.
Okay.
Welcome, Thomas, and take it away.
Thank you.
All right.
Okay, so I'm going to be talking about the opposite end of the spectrum from what Marco's just talked about, which is you've got a single computer, could be a server, could be a desktop or a laptop machine. Probably it's a server. And you want to make good use of the CPU cores that are in that one machine. And so for the past few years, along with many other people, I've been working on trying to make that happen in single node Postgres systems. All right, so my talk's called Parallelism in Postgres 15. I'm going to just give a super quick intro to who I am and why I'm talking to you about this. I started out to work a number of years ago on parallel hash joins. In order to make that happen, I figured out, along with a group of people from Enterprise DB who laid the groundwork for parallelism in Postgres, I figured out that there is a ton of different infrastructure that we needed along the way, and I finished up going away and building that first, and then figuring out how to put together a way to perform joins using all the cores on your machine. But I've worked on all kinds of other bits and pieces in Postgres, and I'm quite interested in systems programming stuff like the kernel interface, and trying to modernize Postgres and figure out how we make better use of memory and I/O and threads and things like that. So yeah, I'm based in New Zealand. My little joke here is that New Zealand has the highest number of Postgres committers in the world per capita. There's actually 2 of us. All right, so I should clear up what I'm talking about with parallelism. There's so many different levels of parallelism in a computer. Everything from a single thread in the CPU, of course, because of the hyperscaler nature of computers these days, and going back quite some time now, that's parallelism. And there's obviously vectorization. I/O parallelism is getting more related to what I'm talking about because it is encouraged by CPU parallelism. But there's also all kinds of ways to network loads of computers together and get a really big database going. Citus is obviously a very good example of that, but there's also the built-in FDW system in Postgres, and there's many other kinds of projects that do massive parallelization of distributed databases. I'm not talking about any of that. I'm talking about a single machine with a whole lot of CPU cores, possibly 1 socket or 2 socket or more sockets, like CPUs with many cores inside them. And how do we make use of those? All right. So it's really interesting to look at the history over the past few decades of parallelism in relational databases. If you go all the way back to the 60s and 70s, there were mainframes that had many CPUs. I don't know anything about mainframes, but I know that it's a mistake to think that anything that happened in the Unix world started there. A lot of these ideas were researched and done on mainframe systems before that. But in the 80s, there was one particular machine that I think is really interesting. It was a Sequent computer that the people at Berkeley who started the Postgres project had access to, and it had a lot of 386 chips in a gigantic box, and they had to figure out how to run queries that used all of those CPUs. So on this timeline here, I've shown Postgres at the top there. You can see that yellow color is Quell, because at the time it didn't use SQL. It used another query language, which lost the competition against SQL when SQL was standardized. Quell sort of fell away. But they got parallel query execution going. And then there was a sort of a time in the 90s where we don't actually have access to the source code in that little window before the modern open source Postgres project began in about 96. But in that dark window, we know that the parallelism in the old Postgres code was actually lost in the conversion to SQL. So Postgres is both very late to having parallel query execution and very early, which I think is kind of interesting. So in the 90s, all of these big, well-known relational database systems went parallel, because that's the time when expensive Unix workstations and servers started having multiple CPUs, and the kernels all started going SMP, symmetric multiprocessing, including, and I guess towards the end of the 90s, that was sort of the arrival of really cheap dual Pentium servers and things like that. But if you move forward to the 2000s, around about 2005, something really interesting happened. And this is a chart that came from, or a quote from Herb Sutter, who was writing in Dr. Dobbs' journal in 2005. He wrote, "The free lunch is over," because that was the point where, if you look at the blue dots there, the single thread performance of computers began to plateau. So your computer software stopped getting faster for free just by upgrading your hardware every year. But the number of cores went from 1, which it had been for a long time, to higher numbers. And obviously we now have machines with many cores. And there are pretty much no, every device, every phone, whatever, has loads of cores now. So if you want to get your stuff to go faster, you're going to have to figure out how to program them, which sounds pretty easy, but it's just not. And parallel programming is notoriously difficult. So we have a category of problems that are sometimes called embarrassingly parallelizable. Example I'm giving here is, suppose you want to paint your fence and or your wall or something like that. And if you want to do it twice as fast, you could ask your friend to help you, and they could perhaps start from the other end, and you could perhaps have 4 people doing it, and maybe it'll be 4 times faster. You can't really scale painting a fence perfectly forever. Like if you invite 1 million people over to your house, you'll start running into contention problems because maybe they won't fit in your garden or something like that. But generally, you can scale pretty well by adding more people to a problem as simple as painting a fence. And then suppose you want to add up a large pile of receipts. Excuse me. So you've got a huge pile of bits of paper, and you're grabbing the numbers and typing them into your calculator. You might get your friend to help you. And so you're going to have to cut the problem into 2 phases. You'll both grab receipts and add them up, and then eventually all the receipts are gone from the pile, and whoever takes the last one, the other person has to wait for them to finish, and then you've got the 2 subtotals, and you add them together, and you've got the result, right? So that's still pretty much embarrassingly parallelizable. We can see how to do that. And we can see that if you add 10 people and they all start grabbing receipts, maybe they start getting in each other's way, accessing the pile, so maybe they need to grab a handful at a time or something like that. And those kinds of things can be seen in all kinds of parallel algorithms. But to move to a trickier problem, I'm going to try to describe a join using socks. So suppose you have 2 piles of socks, left socks in one pile and right socks in another pile. And these socks are numbered, and your job is to match the socks up, and they're all jumbled up. So somewhere in there's a number 7 sock for the left foot, and somewhere there's a number 7 sock for the right foot. How are you going to do it? Well, even doing that with no parallelism, just one person trying to solve that problem, it's kind of tricky. So, you might think of sorting them in some way, and then I could describe a sorting algorithm with socks, and it would be really horrible to listen to. But another way you might do it, which I'm going to try and describe a hash join, you might set up a grid of buckets, 10 by 10, and put numbers on them. And every time you pick up a sock, you check the last 2 digits. And if the last 2 digits on that sock are, suppose you've got 1,000 socks, right? So you look at the last 2 digits, and if it's 07, it goes into box 07. If it's 32, it goes in box 32, right? So in this way, you can take all of the socks in the right-hand pile, one by one, and put them into the right buckets. And when you've finished putting all the socks into the buckets, then take all the socks. It doesn't matter what order you pick them up in, right? Just randomly grab them. Every sock you pick up from the left pile, you find the right bucket. Then you only have to search through the socks that are in that bucket. And suppose it was 1,000 socks and you had a 10 by 10 grid, you got 100 buckets. So there's only going to be about 10, well, the expected number would be 10, right, in each bucket. So and you could add more buckets and make it easier so that hopefully you can just find the matches very quickly. And in that way, you can match together all of the socks and put them in a pile. Now, suppose you want to ask your friend to come and help you. Can you do it twice as fast with 2 people? Well, pretty much yes, because with that algorithm, you both grab random socks one at a time. You both stick them into the buckets, into the right bucket for the right-hand side, and then then you need to wait until everybody involved has finished putting all the right-hand socks into the buckets, right? Because nobody can start the next phase of taking the left-hand socks and finding the matching sock until they know that every sock, there's no socks in somebody's hands still. They've all got to be in the buckets, right? So we only have this one little bit of communication, but otherwise it scales pretty linearly, right? Like the first phase, everyone's putting the right-hand socks into the buckets. Second phase, everybody's picking up random socks and finding the socks in the buckets and matching. In between, there's this tiny moment where everybody has to look at everyone else and say, right, have we done them all before we move to the second phase, right? So that's the kind of thing that we think about when we do parallel query execution. All right. So I'm now going to talk just a little bit about how we make, before I get into how we make parallel query plans, let's quickly review how we make plans in general in a relational database. So a database generally is a typical relational database, not just Postgres, but many other similar systems, is a machine that you feed queries into, and something called the planner takes the query as input, some analyzed form of the query, plus a whole lot of statistics about the tables that it references, and a whole lot of settings that control the costs of things and various options that are available to it, and somehow magically spits out a plan. And that plan, I'm showing there in the middle of the slide as a sort of a tree of operations, can then be used to execute the query. And so you execute the query, and executing the query, you may execute that plan multiple times because, if you use a prepared statement, then it's going to stick around and you can keep doing it. It'll be faster. You won't have to plan it again. And then executing it runs all the steps in that plan against the tables that contain the data and somehow spits out the results. All right. So how does the plan get built in the first place? Well, I'm not going to go into detail because it's pretty complicated, but generally, the optimizer is cost-based in Postgres and in many other systems. The first thing it does is thinks about all the ways that it could access the base relations, the tables you mentioned in your query. It also has to think about all of the different ways it could join the tables that you mentioned if you had joins in your query. For example, if you're joining tables A, B, and C, it could join A and B first and then join the result of that against C, or the other order. Or if there are many tables, then there could be many possibilities. It quickly explodes. And it also has to decide for each join which of the three main join algorithms or strategies to use. Merge joins, where you sort of zip things together that are in the right order, or hash joins, which are a bit like that bucket thing I was describing, or nested loop joins, which usually involve looking at an index, which works if you've already got an index, right? But if you haven't got an index, you might try the bucket thing with the hash join. And there's a bunch of other things to consider, especially involving aggregation, group by, and that kind of thing, and window functions, and all kinds of other complexities that get considered. Somehow we produce all these different things we call paths, which are basically little plans, and estimate the costs of them, and figure out which one wins, and which one is worth executing. All right, and it's based pretty much just on the expected time to run that query. So when parallelism came along in Postgres 9.6 and a few years ago now, and then it's been improved in each release since then, the basic approach chosen for now is to add more options to the planner, and those options involve parallel versions of some of the regular executor operations that we have. For example, a sequential scan is something in normal queries where you just run through a whole table and look at every tuple, right? And you might filter it, but basically you're looking at each block in a table, and which is hopefully in cache, but maybe not. And the parallel sequential scan is the parallel cousin of a sequential scan, which simply gives different blocks to different processes. So each process that's executing the query will look at a different arbitrary subset of the data. It's a bit like with our two piles of socks. If you're scanning one of them, you're grabbing arbitrary handfuls, and you're both, like, maybe there's two processes involved, and they'll both grab arbitrary handfuls until there are none left. So we don't know which socks each of the processes is going to receive. We just know that they're going to grab them on demand until there's none left, and between both of them, all of the socks will be picked up, right? That's the basic concept. So we have this parallel sequential scan, which essentially distributes the data in some arbitrary fashion. And it's the same with an index scan. Then we have a bunch of different nodes, just a few actually, that have a special parallel variant. And that means that there's some communication between multiple processes. Append nodes is an example, and hash joins is another example. And then we have a gather node, which is a thing that collects all of the results from multiple processes, collects them together and spits them out in one process. And that's the way we get results back to, that's going to have to be in there if you want to get the results back to a client. Another thing to talk about is partial and finalized aggregate. So normally in a query plan, I'm going to show examples of this in a second, so you'll see what I mean. But normally we would have, in the example of a simple count query, with parallelism disabled, you would see that here's a sequential scan on table T, which has an aggregate above it, and that's the thing doing the counting. The parallel version of that query plan has a gather node where the answer gets spat out, and above the gather node, you can see the finalization of the aggregate. Below the gather node, we've got multiple processes running, and that's where the subtotals are computed. So when I talked before about about receipts and adding the numbers up, and that's happening in these worker processes, and they are adding some arbitrary subset of the values up, in this case counting, and then all of those subtotals get handed to the leader process, and it's going to do the final, summing and spit out the answer. So the answer should be the same. And generally speaking, we find simple queries like this scale more or less linearly. The more workers you throw at them, the faster they'll go. Especially if you have some filtering going on in those scans, so that the CPU has to do a bit of extra work, and you're not perhaps limited by I/O or something like that. So there's a pictorial representation of 3 processes, where one of them is the leader process, and it's the one that has the gather node. The 2 worker processes that help it run that query just have the lower part of that query plan, and their job is just to get the partial aggregate number. So that shows 3 separate processes adding numbers or counting receipts or whatever it is that table represents. All right. So I'm now going to talk about I'm now going to talk about the way that we can influence the choice between using a parallel query and a regular non-parallel query, like older versions of Postgres would. So one of the most basic controls that affects this is the cost of setting up a parallel query. And there's this arbitrary number 1000, which is a nice round number, which is used by Postgres when considering the cost of any plan to actually start up the parallel worker processes. Now, Postgres is showing its age here. Most other comparable systems use threads and would have a thread pool that would be able to, help out with a query like this. I think we'll eventually get there with Postgres. At the moment, it's still using processes, and that's one of our weaknesses. It's a few problems to solve to get there, but in any case, we somehow need to account for the cost of that. So, for example, on a typical Linux system, it might take a few milliseconds to start up a parallel worker process, which in the scheme of things is not that bad if you're dealing with a large analytical query. And essentially, what we're trying to do here is represent the fact that if you have a large analytical query, if you have regular OLTP type workloads where you're just updating single rows and inserting single rows, none of this stuff ever needs to run. It doesn't really matter. We want to make sure that it looks, there's a bit of a starting cost to any parallel query. So that's what that number represents. But you can set it to 0, and then you'll start seeing all of your queries using all of your select queries using parallelism or trying to, and probably it'll slow down a bit for the very small queries. But it really pays off for the big queries where you get the linear scalability if you're lucky. So the next simple control is it tries to capture the idea that every time a tuple has to be sent from a worker process into the leader process that's going to send the results back to a user, for example, or do further computation on them, there's a cost to that. So, for example, if you tell Postgres that you want to select all of the rows from some absolutely enormous table, it's probably not going to do the scan in parallel in multiple workers, because if it actually has to, if it's really just reading them off disk and sending them back to you, and those worker processes are actually just going to have to first send them to the leader process so it can send them back to you, then it's actually a waste of time, and there's no point in involving parallelism in that. But if the where clause in the query, as simple as this, can be determined to filter a lot of tuples out, perhaps running some expensive computation, perhaps doing some JSON transformation, or something like that, where you're using a lot of CPU, and only spitting out a small number of tuples, then it would make sense to have the parallel worker processes involved in helping you scan that table. So that and the way that estimation is based on having some way to charge you a cost for sending tuples back to the parallel leader process. So those are two really basic settings that you can play with to try to convince Postgres to parallelize or not parallelize queries according to for experimentation or to improve performance. All right, so the next question is, once we've decided we're going to use parallelism or not, or when trying to compare them, one of the factors is how many parallel workers should help with a given query. And the current system is quite primitive. It's based on rules. And this is probably something that'll change over time, but the current system that we've started with is based on some kind of idea of a driving table. That's not really a term that's in the manual, but it's kind of the way I think of it. There's a kind of a rule for figuring out where the biggest set of tuples is coming from that's feeding into a query, and I'll show an example in a moment. And so once you've sort of figured out which the driving table is, that you can either say, well, anytime I do a full table scan on this table, which might be some massive analytical table full of data that you want to crunch, you can actually explicitly set it to always use, say, 7 workers or something on that table with an altered table statement. But normally, the normal rule is based on this heuristic where we have this minimum parallel table scan size, and you can set that. And if your table is at least that size, we'll consider starting a worker. And every time it gets 3 times bigger, we'll add an extra worker, which is a very simple rule. So you can adjust that if you would like to see more or less parallelism according to your table size. And then probably most importantly, because most people who want to see parallelism probably have very big tables full of data, right? That's why they'd be interested in this feature. So they might be probably the most important thing to tweak, to experiment with this stuff is max parallel workers per gather. It says for each gather node, which in many simple queries, there would only be one gather node that would appear in a parallel query. It's capped at 2. And that's kind of because we don't really, like Postgres has some default settings that are based on not knowing anything about the machines it's going to run on. So if you have a 64-core beast or more, then you almost certainly want to turn that up. All right, so I'm just going to show. So here's a query plan shown graphically, which shows a fairly typical example of a nested join. We've got 4 tables being joined together. There's some really big table, and it's being joined against many small tables. Perhaps the big table is sales, and the small tables would be customer and product, and a couple of things like that. So those might be reference tables in some sense. And so the thing that's producing all the tables, that's the thing that's producing the huge number of tuples, that's kind of driving this flow of tuples, in this case, is the thing that we want to parallelize on. We want to spin through the huge list of sales, and for each one, you get the right answer if in each process you go and look up the corresponding customer and so forth. So that I'm trying to explain here that there's one particular table that probably, in many queries, that's the one that's going to be used to drive the rule that selects the degree of parallelism. Okay, I'm now going to quickly run through a couple of different parallel query plan types. And these are focusing heavily on joins, mainly because that's an area that I've worked on quite a bit myself. There are other things that I'm not covering here. All right, so one kind of thing that join that works really well in parallel is a typical inner join where there's some large table that we scan through, and for every tuple we see, we need to go and look something up in some other table. And over on the top right-hand corner of this slide, I've tried to represent how you might think of the time passing when you're running this query. The blue bar shows, in some abstract, I'm not showing the actual numbers here. It's not a real query, but you ought to be able to get something like linear scalability from a query as simple as this. And one thing to note is that we didn't have to invent anything new to make these index scans for nested loop joins work. We just needed to get each process to be given a different subset of the tuples on the left-hand side of this this diagram. So that's where tuples get scattered, if you like, between the cooperating processes. Each process is free to go and look up the corresponding thing to perform the join in the other table, which might be, say, the customers table or something. And between them, they all of the tuples will be processed. Each one processes some completely arbitrary subset until the data runs out. So you might so the green bars there represent the fact that the same amount of work is split up by 3, and a query like that might go 3 times faster. A hash join is essentially similar, except that if it's a very small hash table, if the table being joined against is relatively small, it makes sense to have each worker build its own mini hash table, and it's actually going to run that subplan in duplicate. So every single process involved in this join would, you could think of that as kind of broadcasting the data to each process, but it's essentially running the same plan on one side of this join, and to produce a set of private hash tables that are not shared, and no extra communication is required. I'm showing these nodes as blue because they don't know that they're in a parallel query. They're just doing their normal thing, but the parallel sequential scan is green, and that's my notation on these slides for knowing that it's parallel aware, and it hands out different tuples to each process. So if you look at the time chart on the top right-hand corner of the slide, I've shown that there's a build phase where we build the hash table, and that's not got any. It's not going faster because of parallelism. And then there's the probe phase, which is, if we think of my example with matching socks, it's the phase. The build phase is when we're putting the right-hand socks all into the buckets, and then there's the probe phase where we're going through our socks and trying to find the corresponding ones. That phase can be done. Can be made to scale pretty much linearly, a bit like a scan. Excuse me. So in this, with a join like this, it makes sense if the hash table is very small, not to bother with any communication between workers to get the hash table built. And it's okay to have this duplication when the table's small. But if we try to parallelize both sides naively, and we just put the parallel sequential scans on both sides, we wouldn't actually get the right answer from our query, because each process would build a private shared hash table that doesn't contain the whole set of right-hand socks. So basically I'll just take a sip. So each process would finish up building its own private hash table, and then from some subset of the right-hand socks, and then it would take some subset of the left-hand socks, and they wouldn't, it wouldn't be complete, so they wouldn't be able to produce the right answers. So for that, we need to use a shared hash table, and that involves this 2-phase. And finally, here we see in the time chart in the top right-hand corner that in the first phase is then divided by 3 and goes much faster. That's kind of from the sock example. And then the probe phase is also linearly scaling. And so finally, we managed to get a hash join that scales linearly for both sides. So one of the things that can go wrong with this strategy, and probably one of the things that Postgres uses when they try to deal with large amounts of data at the moment, is memory management. And our memory management strategy is not very sophisticated yet. And that's something we need to do to continue to improve. At the moment, the amount of memory that any hash join, or in fact any executor node, but I'm focusing on hash joins here, can use is determined by the work mem setting. But it's also, and there's also in recent Postgres releases, there's this multiplier, so you can make it bigger by changing that. Surprisingly, one of the problems that we've run into with really large data sets is not actually that people set that too large and use too much memory and that everything melts down. Usually that works fine. The biggest problem we've run into with this type of thing with very large data sets is people having work mem set too low, for the surprising reason that that our main strategy for dealing with very, very large joins is to partition the data first. But then if you've got like very, very large tables that you're trying to build, like hash tables, and you're trying to partition them first, the amount of memory it requires just to track the number of partitions becomes excessive. And we also start doing like strange things like trying to open 1 million files and write partition data out to them, which doesn't work so well, as you might imagine. So I guess one of the biggest dangers at the moment with the current design is that if you're working with very, very large data sets and you're using completely default settings and you don't try and give it more memory to work with so that it can use a reasonably small number of partitions, some of its internal bookkeeping memory and management can overflow, and you can start seeing out of memory errors, which has the maybe counterintuitive remedy that you need to increase your work mem so that it doesn't require so much partitioning. That's a problem that we are going to have to continue to work on and improve. So here are some of the things that prevent parallelism in Postgres. One of them is full outer joins. That's a feature that my colleague Melanie Plegerman has been working on. So Postgres 16 should be able to do full outer joins in parallel. At the moment, those can't be processed in parallel. So if you use those in most queries, it'll completely disable parallelism. Another example is FDWs, so a way to talk to other databases. Most of those don't support parallelism across the network. When you're looking at a table from some other remote database using FDWs, a lot of things like that. There are some plans that can use FDWs well with parallelism, but not all. The use of cursors, because we don't have the machinery required to let you fetch small parts of the data at a time if the data is coming from parallel workers. That's just not something we can do. And probably the biggest one is writing. At the moment, Postgres's parallel query planner and execution it's all based around selects. So that would be in the category of major projects. In fact, I've actually made a list of major future projects in this area that I hope over the coming years people will work on to make single node parallelism more mature. So one of the biggest ones is write queries, being able to insert, update, and delete in parallel. At the moment, this is all just talking about selects. A really large one is management of total memory resources and also I/O and CPU. But for memory, that's probably the most obvious problem at the moment. Postgres is entirely based on users telling the system how much memory individual operations can take, rather than telling the system as a whole how much memory it should use, and then letting it figure out how to allocate that efficiently for all of the parallel queries and even non-parallel queries that are running at the same time. Another one of the things that we need to work on is getting rid of the process model, which has been with us since 1986, the beginning of the project. Essentially, Postgres predates threads in a standardized form, and getting out of the corner that the project painted itself into in early years is going to take some major engineering effort, but it's something we need to do. A couple of other areas that are kind of open problems at the moment are figuring out how to break the current executor design up into a different model so that more kinds of parallelism become possible, which is a fairly technical topic. And finally, at the moment, we're not very strong on partition-based parallelism, where you would break data up and on the fly. That we can do joins that are based on partition-wise joins, where both sides of a join are partition tables and the partitioning scheme matches, but we don't repartition data on the fly to match an existing partition scheme or anything like that. And that's maybe something that we should be researching for future versions. And that is the end of my talk. So thanks very much.
Hey. That was amazing.
Yeah, thanks, Thomas. That that was great. Yeah,
Now
I
we-
learned a lot.
You probably want to. Maybe you're hoping I would tell you all the things that are great and not all the things that are wrong. But one of the things about being deeply involved in a project is your mind is full of the things that need to be improved.
I think that's part of being a good engineer, right? You're always looking, how can I engineer this to be better? Like, how can I improve, augment, adapt? I mean, I don't know. My whole family is engineers. And so our dinner table conversations are all focused on how could that be better? How could that be optimized?
It's all wrong. Yeah.
There was one question on Discord that sounded very interesting to me. Are there any efforts to parallelize on the GPU? And
I have heard of projects that do that kind of thing. I've not been involved in that myself, so I don't want to get the names wrong, but there are people who have talked about that using the custom scan machinery. Yeah.
Okay, cool. So that could help with like machine learning kind of things, maybe.
I'm sure that's true, although I don't know anything about that subject. But yeah,
All right.
the things that I've heard of are more based on feeding data to the GPU for filtering there or something like that. But I don't have any special knowledge of that.
Okay,
Right,
well,
yeah.
I just want to say thank you for being back at Citus Con, for submitting your talk proposal. There were 129 talk submissions. We had a 27% acceptance rate. It was really hard making decisions. And there were some fabulous speakers and fabulous talks that we said no to, but thank goodness that we said yes to yours, because this was fascinating.
Thank you.
So,
all right.
Well, you're going to the Discord?
I am. I'm just on my way there right now.
Okay, awesome. So people can ask you questions there. Thank you.
All right,
and then,
thanks.
Before, what are we going to do next, Yelta? Keep me honest.
We're going to watch a little video because there's also 25 additional on-demand talks, and we don't want you all to forget. Even though you're watching live now, but there's lots of talks, also really good talks, all amazing, and be sure to watch some of those. And we'll show now a small sneak peek of some of those.
We are so happy that so many of you are joining us for Citus Con, an event for Postgres 2023, now in its second year. I want to make sure you know there are 37 talks in this year's lineup. Not just the 6 talks in the 2 live streams, but there are 25 more brand new talks. We call them on-demand talks, and they're going to publish on YouTube at the very start of Citus Con. Lucas Borges is giving a demo about how to auto-scale Azure Cosmos DB for Postgres using Grafana and Azure Serverless. Haki Benita is giving a wonderful talk on unconventional ways to index UUIDs in Postgres. Hedy Dombrovska is presenting on temporal features and time travel. Adi Kumara-Chat is going to cover partitioning strategies for Oracle to Postgres migrations. Bruce Momjian is giving one of his many talks on artificial intelligence and Postgres. Paolo Melchiore is going to teach us how to build a web map using Django and PostGIS. And Chelsea Dole has a great talk on Postgres table bloat. And there's even more. You can find all 25 of the on-demand talks at aka.ms/CitusCon-on-demand.
And now we're going to invite Nasila Puka, who's going to talk about some amazing things. She's a software engineer at Citus. Hi, Nasila.
Hi, how's everyone doing?
So you work at Citus at Microsoft, obviously, and you're based in Turkey, is that right?
Yeah, that's right, in Ankara.
And I heard this is the first time you're giving a conference talk. Is that correct?
Yeah, that's true, and really excited about it.
Good to hear. We're excited to watch you. At least I am, for sure.
I think every great conference speaker remembers their first conference talk. So you are going to remember this day.
Yeah.
We all go through it. It's like a rite of passage. But I've seen you give internal demos particularly when there's a new feature that you've worked on. And I've always thought you're just a natural at it. So I'm excited to hear you dive into benchmarking, which I know is one of Yelta's favorite topics as well.
Yes, yeah. I wrote a few blog posts about benchmarking, so I'm very excited about what you were going to share.
Okay.
Yeah, actually, I did refer to those blog posts myself, so thanks.
Well, Nicela, take it away.
All right. So, hi, everyone. So I'm a software engineer working on the Citus engine product in the Postgres team at Microsoft. And in this talk, you will learn about measuring database performance of Citus and Postgres through the HammerDB benchmark. For me, at the beginning, it wasn't obvious how to even get started with running benchmarks. So hopefully, you will get a beginner tour of the whole process. So let's dive in. I decided to present this in the form of a What I Learned talk because it truly was an experience of learning after each single run of a benchmark. I feel like that's how I want to tell about this to other people. So let's measure Citus and Postgres performance with HammerDB together. Here is a brief outline of this talk. First, you will get a brief intro into the database and the benchmark I used in this process. What are the Citus capabilities we want to measure and how the HammerDB benchmark is suitable for this measurement. Then I will show you how I first configured the benchmark and the Citus cluster, starting with a set of results and interpret them together. You often realize the parameters you wanted only after running the benchmarks. So tweaking parameters based on results is quite common, especially at the beginning. And I will show you how I did that as well. So what is Citus? Citus is essentially distributed Postgres. You can configure a cluster with multiple worker nodes, and then you distribute your Postgres tables through this create distributed table function. The table is divided into these smaller table chunks called shards, and these shards sit on the worker nodes. So basically, Citus is a Postgres extension that gives Postgres scale-out capabilities. And in the title of benchmarking Citus and Postgres performance, I don't mean to say that I have benchmarked plain Postgres as well, but rather that I have benchmarked Postgres with the Citus extension. So in order to run a benchmark, we need a workload category. We need to define that one. OLTP is a quite famous one for distributed databases. It means online transaction processing, and it is a type of data processing that consists of executing a number of transactions occurring concurrently. Used in, for example, shopping, online banking, etc. So Citus is good at OLTP because it routes each query to the worker node which has the shards the query accesses, and is hence able to distribute the workload of concurrent queries among the worker nodes. How good is Citus at doing that? Well, that's where HammerDB comes in the picture because it helps us measure that performance. HammerDB is an easy-to-use open-source benchmarking suite for databases. Its benchmarking suite for OLTP is called HammerDB tproxy, derived from the TPCC benchmark standard. And as of HammerDB 4.4, there is support for Citus through this PG Citus compat flag. Essentially, all the tables will be distributed before running the benchmark through the create distributed function I mentioned before. Note that HammerDB tproxy is a full benchmark suite. An application is provided to you which will run the benchmark. You configure the benchmarking application to run against your database server. And once it's done running, it shows some numbers. And I focused on this NOPM number to indicate how good the run was. NOPM, new orders per minute, is actually around 43% of all transactions, and that's because TPM, like the transactions per minute, records all the transactions, commits, and rollbacks during the measuring period on the database, whether HammerDB induced those transactions in the testing or not. Okay, so let's start and learn along the way together. So we want to measure Citus capabilities and at the same time already start with the aim of achieving a high NOPM throughput. Let me also let you know here that the benchmarks run in Citus's home on Azure, which is called Azure Cosmos DB for PostgreSQL. It's very easy to configure the cluster you want in the Azure portal. And I wanted to start with a powerful cluster. One with 10 workers is really powerful enough to show scale-out capabilities. The coordinator is a machine with 32 vCPUs and half terabyte disk. This is the minimum disk size, I believe, you can configure in the Azure portal, but no data will reside in the coordinator. We just care for a powerful coordinator in terms of vCPUs. The workers, on the other hand, are 16 vCPU machines with 2 terabyte disks each. And in the rest of these slides, I will be referring to such a configuration as 10, 16 plus 32 for convenience. Now, what about the benchmark parameters? Well, there's two main parameters I will talk about here: warehouses and virtual users. So let me start by explaining the warehouses concept. As I mentioned before, HammerDB proxy is based on the TPCC specification, the story of which is fulfilling orders from customers to supply products from a company. It's a typical OLTP example. The company keeps its stock in warehouses. The warehouse size is around 100 megabytes. So the more warehouses we configure, the larger the database schema will be. And since we picked quite a powerful Citus cluster to begin with, we expect it can easily process the increased level of transactions that a larger schema comes with. And leading my explanation towards the virtual users concept. So virtual users are essentially OS threads, and they will open as concurrent connections to the database. Each virtual user selects a warehouse, so we want at least one warehouse per virtual users in order to avoid lock contention. Now, Azure Cosmos DB for PostgreSQL has a limit of 1,000 concurrent client connections. So I will utilize all I have at hand and go with 1,000 virtual users and 1,000 warehouses, which is the minimum number of warehouses needed. It's around 100 gigabyte and it will build fast. So I started with that. So now let's see some numbers. These values here are coming from the benchmark run with 1,000 warehouses and 1,000 virtual users. Essentially, we have constantly 1,000 concurrent connections to the database. The y-axis shows the number of orders per minute, for which higher is better. And the x-axis is showing the different cluster sizes, starting with 10 worker nodes, then 12, 16, and 20. The green color shows results with a non-HA cluster, whereas the blue one shows HA cluster results. So let's interpret these results together. I'll start with the lowest NOPM in this chart, which is 700,000 new orders per minute. actually, even the lowest number here is still quite a good result, given that the numbers I've seen around for this number of cores are in the 200K limit. And the result I loved seeing was this slightly above 1 million NOPM. And with these benchmark runs, the minimum cluster size to reach it was with 12 workers. So as you can see in the graph, and 12 workers, each 16 vCPUs each, plus the coordinator amounts to 224 vCPUs in total, which it performed great on giving 1 million NOPM result. You can't help but notice that when HA is enabled in the cluster, there is some performance overhead price to pay. That's because there is an extra latency at the end of each transaction to make sure the backup server has the right changes. But we notice here that the HA overhead decreases as the number of workers increases, starting from 23% HA penalty with 10 workers and up to almost negligible penalty with 20 workers. And the reason is that the busyness of the cluster has an effect on HA impact. And when the nodes are so busy, then there are replication struggles. Hence, the HA overhead gets bigger. But with more worker nodes, like in the 16 and 20 worker nodes case, cluster busyness decreases. So they handle the HA overload much better. And it doesn't actually give an overhead in the performance in terms of NOPM. And another interesting insight on this graph is that if you look at the green columns, NOPM is improving from 10 to 12 workers, but it's the same from 12 to 20 workers. The reason is that with 12 worker nodes, the cluster is actually doing the best it can to take out of 1,000 concurrent connections. This number, of course, is enough to properly handle the load. And we understand here that in order to properly utilize more cores that more workers come with, we're going to have to fire up more than 1,000 connections, meaning that we want more virtual users. And so let's talk about the first major change we're going to make here, increasing the number of concurrent connections. As I said, we want to keep the powerful 16 and 20 worker clusters busy as well. And we want to utilize the resources in order to maximize the NOPM throughput and properly measure the database capabilities. I mentioned that we do have a default limit of 1,000 concurrent client connections for Azure Cosmos DB for PostgreSQL. And to change this limit, we simply reach out to Azure support for an increase. I went for double the connections since we now have 2,000 client connections available. Let's see some results with 2,000 virtual users and again 2,000 warehouses, which is the minimum needed for this amount of users. All right, so I went for a line chart this time, simply because I was amazed by the increase in NOPM result, and I feel like a line shows that best. So these values here are coming from the benchmark run with 2,000 warehouses and 2,000 virtual users. Let's recap here that essentially we have constantly 2,000 concurrent connections to the database. So the y-axis here is again the number of orders per minute, which is the higher the better. And the x-axis is showing the cluster size again, starting from 10 workers, then 12, 16, and 20. There's a single line here because I am showing results for non-HA clusters. We see a clear rising trend in NOPM, and we reach a whopping 1.75 million number of orders per minute with 20 workers, amounting for up to 352 vCPUs in total. And this graph shows clearly that Citus delivers on the promise of scaling out, because we have added more nodes to the cluster and the performance has gone up. Something important to note here are the relatively lower numbers on 10 and 12 worker nodes. That's because from the previous benchmark, clusters with 10 and 12 worker nodes had already done their best with 1,000 virtual users. And clearly, they now have some headache with 2,000. And it seems that they don't perform that well with this higher benchmark load. To be honest, the 510K number can be higher here. So the data distribution was not as good as in the other cluster sizes. So you see, with benchmarks, often you realize the parameters you wanted only after running them, and they take a lot of time to rerun again. So I guess I just didn't have time to rerun this benchmark and got stuck with this 510K result. But still, they are not bad numbers. They just can be better. And now let's focus more on the good part of the graph. 1.31 million NOPM with 16 worker nodes and 1.75 million NOPM with 20 worker nodes. The numbers are great, and to make sure that we have utilized the cluster resources properly, I went ahead and looked at CPU utilization graphs. It turns out that with 16 workers, CPU utilization is around 85 to 90% in all workers, just good enough to perform well and not have a headache. And the load is very well distributed. In the 20 workers, as expected, the CPU utilization is lower since the cluster is bigger and can handle the load better. It was around 75% in each worker, again, with a good load distribution. And it actually seems here that we can push this 20 worker cluster even further, but I stopped at 2,000 virtual users for now. Let's do some other parameter tweaking here. I already mentioned that I have looked at CPU and disk IOPS graphs, and these graphs provide a really good way to understand better how the benchmark went and to change the parameters to values that will probably yield some improvement. For example, if we noticed low CPU usage, then we increase the benchmark load. So I already did that by increasing the load from 1,000 virtual users to 2,000. Another example is that if we see unbalanced CPU usage, meaning that some of the workers are getting more load than the rest, then we do something to balance the data better in the cluster. Or if we notice high I/O activity that is really wearing out our cluster, we find a way to reuse some warehouses to reduce the I/O activity. So let me go further. Let me go into further detail for these last two cases. One of the most important configuration parameters that influences the data balance in the cluster is the shard count. It's a simple math trick, really. To divide data load evenly among workers, shard count should be a multiple of the number of workers. The default one in Azure Cosmos DB for PostgreSQL is 32. So immediately you might look back at our benchmark results and think that, okay, 32 is only divisible by 16 and not by 10, 12, or 20, which are the other cluster sizes that we used in the benchmarks. So let me show you an example on the 2,000 virtual users benchmark for a cluster with 20 worker nodes. This is the CPU utilization graph. The y-axis is showing utilization in percentage, and the x-axis is just time progressing in the benchmark. All these lines here belong to the 20 worker nodes, the coordinator, and the benchmark driver. So I mentioned the amazing 1.75 million NOPM result. But you see, I didn't immediately reach that. When I first ran the benchmark, I used the default shard count of 32. 32 shards in 20 workers means 12 workers will get 2 shards each, and the remaining 8 will get 1 shard each. So you can clearly see here that the 8 workers with lower data load of 1 shard each have around 45% CPU utilization. So I'm talking about the cluster of lines here in the graph that is in the lower part of the graph. And in the upper part of the graph, you see the other 12, for which they have higher data load of 2 shards each, and they have much more CPU utilization, with one of them actually maxing out. I labeled as worker 1 here. This configuration yielded 1.22 million NOPM at first. Still, it's a good number, but after simply changing the shard count to 40, which is divisible by 20, the result went up to 1.75 million. So we're talking about 500,000 new orders per minute more here. And this is really one of my favorite examples on tweaking parameters because it's really simple and it was just super effective. And the last parameter I want to talk about here is the all warehouses one. So by default, each virtual user selects a warehouse at random. And since the pick is random, this doesn't ensure that all warehouses will be used. Setting this all warehouses parameter to true means that the virtual users select a new warehouse for each transaction from an available list divided between all users at the start of the benchmark. So this ensures that all warehouses will be used. Now, obviously, this means that I/O activity will be higher. And I ran into an incredible manifestation of this. If you remember, I mentioned that the minimum cluster size I needed to get 1 million NOPM was with 12 workers, 224 vCPUs in total. I ran into this all warehouses parameter importance while doing some experiments with the same number of virtual users, 1,000, but with 10,000 warehouses. So this is the per data disk max IOPS percentage graph. The y-axis is showing utilization in percentage, and the x-axis is just time again progressing in the benchmark. And again, all these lines here belong to the 12 worker nodes, the coordinator, and the benchmark driver. All warehouses parameter was set to true, as it worked well for 1,000. But little did I know that for 10,000 warehouses, I/O activity would be crazy and reach the machine's maximum input-output operations per second. This really gave a headache to the cluster, and I didn't see the 1 million NOPM result. But after setting all warehouses to false, I/O activity calmed down, and allowed us to achieve 1 million NOPM again. So let me show you that more clearly with another graph. It's the last graph, actually. So these values here are coming from the benchmark run with 1,000 virtual users. In the 12, again, with the 12 node cluster. And the y-axis still shows NOPM, but the x-axis this time shows the number of warehouses. 1,000 is around 100 gigabyte of data, whereas 10,000 is around 1 terabyte, and 20,000 is 2 terabytes, clearly not fitting in memory. So the green columns show the results when all warehouses are used, whereas the blue ones show the results with all warehouses set to false. And as it's noticeable from the graph, NOPM result has decreased as we increase the number of warehouses in the case when we use all of them. Obviously, the I/O activity is so high that we just max out on disk I/O apps. Setting all warehouses to false, however, doesn't affect our 1 million NOPM result at all as we increase the number of warehouses. And note that this case is also the closer one to the real world scenarios, because in the real world workload, it's very rare that you are continuously reading your entire data set, but rather you're just reading a part of it. So what I mean is that setting this parameter to false is giving us reliable and normal results. So I hope I was able to communicate my learnings from the benchmark results, and I'd like to share with you some more overall reflections on this experience as well. It's always good to see and read some documentation before starting. I don't recommend diving deeply into it if you're just a beginner, but just good enough to clarify your ideas and also learn a bit about the cluster capabilities. Just enough to start somewhere somewhat meaningful, not perfect. You will most probably study your results and run benchmarks over and over again after changing parameters to your desire. It does take time to run these benchmarks, and it's almost impossible to run all the different configuration parameter combinations that you'd like. Actually, personally, I have more to learn on Citus and HammerDB tproxy benchmarking. It has been a beautiful journey, and I hope to continue it in the future, to be honest. And I'd like to share my main references for this talk and my work on benchmarks. HammerDB's official documentation, of course, it's easy to follow, brief and concise, and also this great blog post on how to benchmark the performance of Citus and Postgres with HammerDB on Azure, which actually points to some really handy scripts on how to actually initiate and run the benchmarks. And with that, I conclude my talk. Thank you all for your attention. It's been a pleasure.
Thank you, Nisela.
Yes,
That
thank
was
you.
awesome. You did it. Yes.
Yay!
There's more questions than we have time to ask you because we are running a bit behind, but I know Yelta absolutely wants to ask one or two of them. And then there's more waiting for you in the Discord, okay?
All right.
But yeah, that was awesome.
So one question I had is, I mean, the numbers you showed, they're great. They're really high. Is there any way you think we can get even higher? Do you see sort of possibility, or did you sort of reach a ceiling where it just wouldn't go even if you added more nodes or something like that?
Yeah, so that's a great question, and you actually touched me on my soft spot, because I just had to stop somewhere during my work with benchmarks, but I still, as I also mentioned in the talk, with the 20 workers benchmark, the CPU utilization can get higher, but I used 2,000 connections and didn't try above that. So I believe that by increasing the number of parallel connections, like concurrent connections to the database, and increasing the number of virtual users, the 20 workers cluster can be, resources can be utilized more, and I believe we can reach a higher NOPM result. And if not that, if the cluster would wear out just by adding more nodes or increasing, configuring the nodes, the worker nodes differently with more vCPUs, I'm really confident that we can reach like 2 million plus NOPM numbers. But I didn't have a chance to try that out yet, but I hope to in the future.
Very, very cool. And you mentioned people can run these benchmarks themselves. How do they do that?
Yeah, so there's like an open source tool, Citus benchmark, that has a good documentation on how to run the benchmark yourself, and it actually has some great scripts that will just create the cluster for you and run the benchmark and delete the cluster after running the benchmark and just give you the result back, and it's just really handy and easy to use.
All right.
Okay,
Cool.
Jelte, that was totally a
Yeah.
leading question. Yeah, but it's important to, and maybe you can share that link in the Discord, Nisela.
Yeah, please do. And there's
Okay.
also some other questions in the
Sorry.
Discord, so be
Cool.
sure to answer those.
Awesome. Well, thank you very much, Nisela.
Okay, so I'll be going to Discord. Thanks. It was a
Awesome.
pleasure.
See you there.
Ciao.
Bye.
And now it's time to welcome Boris Mejias. Did I say your name right, Boris? Did I get it?
Absolutely. Yeah, perfectly.
Okay.
Very good.
So for those of you who don't know Boris, he's a Postgres solution architect at EDB. I first met Boris at PGConf.eu in Lisbon. I was giving my first Postgres conference talk, and you were in charge of my talk track, and you just made me feel so welcome and comfortable, and it was pretty awesome.
That was a nice talk, I remember as well. I always go to see your talks whenever I can. So.
And then Jelte, you and Boris know each other. You've met before.
Yes. Yeah. I also met him at my first conference talk. So that was he did an amazing talk about metal. He was
yeah,
very
well,
funny. I remember it being very funny. I laughed very hard.
That was
as
an
in like the
uptime
gold in my
conference in
ring, or as
Amsterdam.
in heavy metal?
He was making a joke that bare metal was the best because he liked metal music.
Got it.
For deploying Postgres. So
For
no
deploying
containers,
Postgres.
no virtual machines, just bare metal.
So for those of you who are in the audience and don't understand what Postgres storytelling is, you're in for a treat. This is a highly unusual conference talk. It is most certainly not dry. So I recommend that you stay, and let's listen to Boris tell us a story about Postgres. Take it away.
Thank you. And hello, everybody, actually, who is watching this recording afterwards. And thanks for coming to try to see this presentation. It's not a typical technical deep dive with a fast pace that is going to find the answer to a very heavy technical question. This is really, as Claire was saying, storytelling. So it has its own pace. And if you want to stay, it is probably because you are related to the story. It has happened to you maybe before, or this is a story that could happen to you if you're not careful about taking care of your Postgres database in the best possible way. So this is the most fear, or one of the most fear problems in Postgres, which is the wraparound problem. So Iron Maiden has fear of the dark. The Postgres users, we have the wraparound problem. It's kind of a mystery. So I'm going to try to explain what it is in this presentation. So this is Postgres storytelling and support in the darkest hour. And this presentation wouldn't be possible without the help of Scarlett Riggs. She has magical talent for making the illustrations. So all the illustrations come from her. And well, my name is Boris Mejias. I'm originally from Chile, but I live in Belgium since the beginning of the century. And I worked and lived in Brussels before, and I come back regularly to Brussels to meet some friends. And it is in Brussels that I met Monica DBA. So Monica DBA is actually one of the most talented people that I ever met in Postgres. She's not just a support engineer, not just a DBA. She really knows a lot about Postgres, and she should be probably appearing in Postgres Person of the Week, if you know that blog. And she works together with Kevin. Kevin is her senior DBA, but actually Kevin is always learning from Monica. They work in a company in Brussels where they do support plenty of other database systems, Oracle, MySQL, and other things. But the Postgres team is the smallest one because it's the newest one in the company. Things are migrating to Postgres. So one of the things that Monica has to do together with Kevin is to enhance whatever has been deployed already by other people, developers, software engineers that were trying to do their best with Postgres. So she brings the expertise to the company. Now, with Kevin, they do have some common practices to kind of like instead of doing a team building, because it's just a short team, they do continuous team building. So every Thursday they go to the pub and the night. And although this story is going to happen on Friday evening, it starts at the pub on Thursday evening when Kevin was asking the question to Monica, Monica, can you explain me a little bit more about what is this wraparound problem that I heard of? And Monica said, okay, well, let's order a beer first and let me explain you what this is all about. But before explaining you the problem, I need to explain you how does Postgres work with the transactions. So everything in Postgres happens inside a transaction. This is one of the basic stuff for having ACID properties: atomicity, consistency, isolation, and durability. So you have the transaction that starts from 0 and goes growing and growing and growing with a number. At a certain point, you're going to have your transaction writing some rows in your table, updating them, deleting them, doing whatever you want to do with it. And that transaction is going to be identified in time with that number. And everything that happened before that number is going to be considered to be in the past, and everything that happens after is going to be in the future. There are, of course, all the kind of things, but in the interest of simplicity, and because we're at the pub, we're going to just ignore all the rest. Just concentrate on this identity of the transaction. And then Kevin says, but this is an integer, right? A number. How far can you go with this number? Is it infinite? No, of course not. It is a big integer, so you are fixed with a size of 4 billion, which is the maximum value that you can get with a big integer. So Kevin said, wait a second, you're not telling me that in a Postgres server, you can only run a maximum of 4 billion transactions. Of course not. What is going to happen is that when you get to that maximum value, the value is just going to wrap around. So is that the problem? No, that's just how it works. You just have a fixed amount of numbers, and you need to get back to your starting point, which I think is number 3 or something based on the implementation. So let's get another beer and let's try to explain what it was going to be really the issue of the wraparound. So what happens is that at this point, our beers are empty, right? So we need to order another beer. And in the same thing that time flows from some time, like a lot of years back in the past, and then it's going to go continuing almost to infinity in the future, as far as we know, we still measure time with a clock. And a clock is also a limited amount of hours. Some people use digital watches, which has 24 hours, or clocks that I like, which have only 12 hours, are enough to measure time and know what is past and present according to our context. So our beers are empty, so let's order another beer. What time it is? It's 9 o'clock. Okay, so let's ask the barman, hey, barman, can we still take orders? And the barman answered, yes, of course, we are taking orders until 11. So it is 9 o'clock, and 11 is a number that is larger than 9, which means that it's in the future. No problem with that. Everybody understands that. Good. They got a beer, they got another beer, and then finally it was time to leave because they didn't serve any more beers. So they went to another pub. They entered the pub and they said, okay, barman, can we still order beers? And then barman said, of course, we take orders until 1. But 1 is a number that is smaller than 11. But everybody knows that it's in the future because the clock is going to wrap around on number 12 and it's going to start back to number 1. But it's so close that the proximity will tell us that this number, it doesn't matter whether it's in the back or not, it is going to be in the future, you know? So that's how it works. All right, said Kevin. So this is nice. So what is actually the problem? And then Monica had to explain something that happened in a party that she was. It's a psychedelic trance music party. She was dancing. It was 3 a.m. She was starting to get thirsty again. And she said, okay, I'm going to order a beer. And she went to the barman. And before she could ask, somebody else was asking like, hey, barman, can I order some beers? And the barman says, of course, we are taking orders until 1. It was 3 o'clock already. And he was taking order until 1. But remember, this was a techno music party, which lasts until 1 p.m. the day after. So that's why it was confusing, because the context, the visibility of your time is larger than what you have expressed as your context for knowing what is in the past and what is in the future. So If it is 3 o'clock and you're taking orders until 1, what does it mean? And this is the wraparound problem, which happens in Postgres when you're not able to understand that your transactions has gone beyond your visibility. I still don't understand how does Postgres fix this, says Kevin. So what happens then when it wraps around? Well, Monica said to Kevin, think about the following situation. What if you were an archaeologist and you find a mammoth, in Spanish, un mamut, a mammoth, in the permafrost? Well, I know it's not just as permanent as we thought, because with global warming, this thing is melting. But what if you found a mammoth in the permafrost? And Kevin started to think and said, well, I think I would say, like, this mammoth looks like an elephant. Think about time. Think about this in the context of time. You will have to say, this mammoth is from the past because it's frozen. It's completely frozen. So it cannot be that just died recently. It's not in our context of time. It is really way beyond in the past. And this is how Postgres fixes the issue with transactions. When transactions are not in our context of whether it's too close in the past or too close in the future, it just freezes the whole thing. So everything that is outside this is going to be considered frozen. And this is done by the process vacuum. When vacuum is cleaning up dead rows and whatever, it's also going to see whether a transaction is not being used by any, a transaction ID is not being used by any running transaction. And so, okay, well, this one can be put in the past. And this is how it's fixed. Wow, that's clever, said Kevin. I like this. So you just need to make sure that your vacuum process is able to freeze these transactions so that you don't have anything affecting the visibility of the rows. Exactly. That's it. All right. So that was the story for Thursday evening in the pub. Nice conversation. So what happened on Friday is that, well, Kevin goes bowling on Friday evening, and Monica just go and have some fun and do some other stuff. And she was preparing some last measurements because of these talks that they have on the pub. She decided to add some monitoring system. And then she put it, and immediately after putting the monitoring system, the alarm started going off, and there is some alert. Kevin was worried. So what happened? And said, well, it's just a thing that I set it up to monitor issues with wraparound. We are having some problems with the visibility. Okay, said Kevin, I would like to help you, but I see that I'm not going to be just providing anything else that's emotional support, and I really need to go to the bowling. Of course, I know. But before you go, why did you ask me actually yesterday about the wraparound problem? Oh, said Kevin, it was actually David, the software developer, who asked me about that yesterday and whether we were monitoring that or not. David is kind of a pain in the neck and other parts of the body, actually. He always thinks that he's smarter than all the rest, and he always tries to do his own stuff because he knows better, you know? So Monica started to suspect something that David was doing in his own stuff and his own servers, and she needed to probably handle it with care. So Monica said to Kevin, please go enjoy your bowling. I will stay here, and I'm going to probably find something, and I will let you know. So this is the monitoring that Monica was putting in place. She will go to the PG_database table in the PG catalog, and she will check for all the databases the age of the value of the database frozen XID. This is the oldest visible transaction ID in the entire database. Remember that the instance has multiple databases. So per database, you will identify something that the age is going to be larger than the value of the auto vacuum freeze max age. This is the value that vacuum uses to kind of panic and say, like, oh, we have something that is older than what we tolerate. By default, this is about like a 200 million. So the spectrum that Postgres uses is 2 billion, because there are 4 billion. 2 billion values back are the past, 2 billions are the future to the front. So 200 millions is kind of about like 10%. Enough to have like a 90% of time to fix the issue. So at this point, vacuum is going to start like freaking out and trying to freeze as much as possible. But everything that goes beyond that, it means that the vacuum is not cleaning up properly. And that's why the alarm went off, because you need to have some manual intervention at this point. So Monica started to think, okay, I know now that I have this database that went beyond the proper value that's safe. So I need to investigate which are the oldest tables that hasn't been frozen yet. They are old enough to be frozen, but they haven't been frozen yet. She went then to the PG class table, where you can get the table ID, which is the OID, the name of the schema, what is running, the name of the table itself, and then its particular relational frozen XID. This is like the database frozen XID, but this is for the table itself. A relational table is exactly the same in Postgres. She doesn't search for everything, of course, because there are indexes and stuff like that, but she will search for everything that is a table, a relation, and a materialized view. And then she's going to, again, ask for the age of each of the table and order descendantly, so that she will find the first one that she needs to investigate. And of course, she found one. Okay, how do you fix this? There is one way of running, like in panic mode, vacuum freeze, yes? But this one is too aggressive. It's going to be kind of generating a lot of walls, and it's going to imagine that this value of auto vacuum maximum freeze age is 0, so everything has to be immediately frozen. Too aggressive, but a normal vacuum should solve the issue, no problem, because vacuum is going to look at those old rows and it's going to freeze them if it is necessary. So she ran vacuum, and she thought that the problem was okay, fine. We'll run vacuum manually to be more aggressive because auto vacuum for some reason is not doing the job, and let's check again. The problem was not solved. She did again the same ordering, and this table was still at the top and the age was increasing. So for some reason, vacuum was not able to freeze these values. And this is because probably there was a transaction looking at this table and blocking some of the visibility of it, preventing from every freezing action, like in the problem of the techno music party. So what happened? She said, okay, if there is something taking the log of this table, I probably need to check in the PG start activity. So she went there, and there are some important values that you can check for every backend inquiry that is running, which is, first of all, the process ID that is running. When did the backend started? This is when the first connection was established, and then you can run multiple transactions in that backend. When the transaction started, which is the XACT transaction start, and then when the query started, yeah, the last query that is running, they are investigating. Then this is you will find it in the stat activity. And then a lot of people are actually worried about long-running queries, but in this case, for visibility, it is actually the transaction that is too long running for too much time. So you need to worry about the moment that the transaction started and measure how much time it's been running. So you do it with now or current timestamp minus the start, and you're going to get for how long a transaction is being running. This is more important than long-running queries, is long-running transaction. Then, of course, you're just interested on the values that are from a client backend and where the transaction start is not null, so you don't get extra information on your table. And you are going to order them by the longest running transaction descendantly. So you will find which transaction is running for the longest. And then she found there was one transaction doing some reporting for 8 hours already. A lot of these were big tables, like 2 terabytes each table. Yep. So Monica said, okay, I found a very long running transaction that probably is affecting the visibility of this table, which is getting too old, and I need to freeze it. How do I make sure, how do I find some evidence that this is really the transaction that is affecting the visibility? Aha, logs. So she went to the table of logs and she searched for, is there anything matching this process ID that I just found on the table ID, which is the relation here in this table, that is actually affecting the visibility. So she just searched for whatever comes in by matching this table in this long-running transaction. And she found something. Okay, so this is the one. It is Friday evening. Everybody's gone. The lights even are out. I will just terminate this backend. The reports can be built during the weekend. I need to fix this issue with the vacuum freeze. This is what she did. She ran vacuum and she went for a coffee. So when she realized that she needed to have some coffee, she stood up. And then these buildings, they have some sensors that after a certain hour, if nobody moves, the lights are out. This is why everything was in the dark. She doesn't mind. I mean, she's not like she's not afraid of the dark. So this is just the moment that she realized that, oh, wow, this is quite late, but I still want to do some other stuff. So more coffee. She got her coffee. She went back. This is still Davy's system. So probably there is something else there. And then she needed to figure it out. So she continued. She checked again for the databases, which one has a value of the oldest row that is still beyond this limit, this healthy limit of the auto vacuum freeze maximum age. And she found that still this database was having an issue, not with the same aging, yeah, but it was different. So it was improved after vacuuming this table, but it was still there a problem. So she ran again the same query to identify which is the next table giving me an issue. She found it. She said, okay, probably another issue with some long-running transaction, long-running query affecting visibility. But she didn't find anything in the pgstat activity. Okay, so let's try to find any log at all that it kind of got there hanging affecting this particular table. So she didn't have any process ID at the moment to match, but she just wanted to search anything on that table. Nothing, absolutely nothing. So what could prevent auto vacuum from cleaning up the oldest table? So this was kind of pissing her off, because she didn't understand why, if nobody's touching a particular table, the table is not being healthy enough to freeze all the old transactions. So she meditated. This is a good exercise for everybody. Breathe, concentrate, think about a nice drink, nice music, nice people. And then suddenly might be that you find out what you need to do next. Checking a break is always good. Step back and then come back. She realized, okay, I need to look at the statistics of the table. So she went to the pgstat user tables and she looked at the following information. How many tuples were inserted in this table? How many tuples were updated and deleted? Then how many live tuples are in the table? And how many dead tuples? That is going to trigger the auto vacuum, because when you have too many dead rows, you're going to have to clean it up, vacuum them, okay? So she also wanted to see whether there was something wrong. Maybe somebody disabled auto vacuum on this table. So she checked for the last time that vacuum was run, last time that auto vacuum was run, and how many counts were there. The table was the payment logs, okay? A very large one. And then she realized that the amount of inserted rows was the same as the amount of live tuples. That means that this was just an insert-only table. So 7 billion rows was like 4 terabytes of data in this table. So it was a very, very large table, but without any dead rows. So that means that vacuum was never really triggered. But still, auto vacuum was running multiple times. And the last time this was Friday evening in February. And the last time was really recently. So auto vacuum was really trying to clean up this table, although there are no dead rows, but it was trying to freeze the old transactions. But it was not just able to do that auto vacuum. Then she realized, which version of Postgres is this one? And then she checked for the version, is version 13. Ah, she said, there's still an issue with this one. So what happens is that when you have an insert-only table, the vacuum is only going to run when it surpasses this value of the auto vacuum freeze maximum age, and it starts to panic and say like, oh no, I need to do this because we haven't vacuumed this table all along. In newer versions of Postgres, 14 or 15, this is why you have to upgrade. Postgres will do it after a certain amount of inserted rows, even though there's no dead rows, it will still do the vacuum just to freeze all transactions. So the problem is that when it triggers this value, it's already kind of late, and multiple rows, multiple tables are going to have the same issue if they're all of them inserted only. So what is happening is that auto vacuum is trying to clean up as fast as it can, but the table is still growing much older. This is like trying to vacuum in a party. Imagine that you are in a party and then trying to clean up, and the party is making more mess faster than we are able to actually clean up the room. So this is what is going on. So she said, okay, probably if this system was set up by David and we haven't been able to touch this system before, the auto vacuum is not being tuned yet. Aha. So this is what Monica figured out. I have found the issue that this table is not being vacuumed enough or not fast enough. So I need to check the following parameters. Auto vacuum cost delay, which is by default 20 milliseconds and needs to be much shorter. So she reduced it to 2 milliseconds, which is one of the new default values. And the auto vacuum cost limit was actually set to -1. Usually -1 will mean infinity. But in this case, it just means that it's not being set up and it's going to use the default one of vacuum cost limit, which is about 200 units of work. Not enough. So she increased that one to 4,000. The idea is that your auto vacuum will be able to run much faster, do a lot more work, and then continuously advancing and making progress. So it's like instead of vacuuming in a party with a small vacuum cleaner, you will be able to vacuum with a larger one and do a lot more time in between. There's no reason to say like, oh, stop the party, everybody goes out, I need to clean up, and then you can go back and continue the party. Not necessary. Auto vacuum will do it for you. So never disable auto vacuum and try to tune it properly. So this is what she did. And she said, well, I'm not going to even run vacuum freezer or vacuum manually. I will just let auto vacuum fix the problem for me, because that's his job, you know? So this is what she figured out. She make sure that no other parameters were set specific for that particular table, so the global values will be enough. And she went for another coffee. Again, lights went on so that she could safely walk to the kitchen, then get another coffee. Because she was still not happy about the entire thing. There was still something else that she needed to investigate, because this is David's system. So auto vacuum started to run, multiple process, and the age, it was not fixed immediately, but it was decreasing. It's like Dorian Gray. The table was getting younger and younger and younger because the oldest rows were being frozen. Very good. Auto vacuum fixed the problem on its own. But Monica wanted to continue investigating before ending the day. So she went to see the logging of the queries, and she figured out that every minute, so this was probably a cron job, there was this query trying to figure out the age of the databases. The query was run from a remote machine, so probably Dave's machine, trying to monitor this thing. And it was saying, give me the database, give me the current transaction ID, and then get the distance from the current transaction ID and the oldest transaction ID in this database to calculate the age. A reasonable thing to do, I would say. But the thing is, Postgres will never increase the transaction ID unless you're writing something. It's only useful when you insert, update, delete, or do something like a DDL. If you're just reading, it will never create a transaction ID for that particular one. There's some other stuff that are extra, but in the interest of simplicity, I will just leave it like that. Of course, it will generate a new transaction ID if you explicitly ask for it. And this is what David was doing. He was asking for a new transaction ID for the current transaction, although it was not necessary because this was just a reading transaction. So it was consuming transactions ID every minute. Not that it was going to be a real problem. I mean, there are not as many minutes in a day to affect really the problem, but it's bad practice. The best is to just use what Postgres is giving you to calculate the age of a database, which is this function age with whatever XID you provide. It can be from the database, it can be from the table, it can be from a row. You will know the age by using this function. So she did three things after this. She sent a message to Kevin, not to worry about, so that everything was fixed. She sent a message to Jean-François, the boss, asking for upgrading all the system from Postgres 13 to at least 14 or 15. And she sent a message to David to please stop running select TXID current just for the sake of it. Okay, so Monica was happy. It was time to go for another coffee, she thought, but no, it's already too late for a coffee. She went for another beer at the pub. And this is where I met Monica, actually. And she started to tell me about the whole adventure about Friday evening and Thursday evening. And this is how I got to know about this story. And that's why I can tell you about it now, right now, thanks to this nice encounter between people. That's all for me. So thank you for listening. And I hope that you enjoy the story and maybe you learn something about wraparound problem. Thank you very much.
Hey. So I guess we have two people to thank for that amazing talk. You, obviously, for
Thanks.
putting it together, conceptualizing it, delivering it, but also big shout out to Scarlett Riggs. Wow.
Yes,
That's
she is really good.
the artwork is just beguiling. It really is.
Thank you. I will pass the message. Absolutely.
Yeah, it looks amazing.
So one of the things I wanted to say, in addition to seeing you present today, I wanted to let everybody know, and I'm going to pop this up here really quickly, that you are also going to be a guest on Path to Citus Con on May 3rd. So that's coming up in a couple of weeks. You and Alvaro Herrera are going to be joining us to talk about why giving talks at Postgres conferences matters. And because you've obviously been doing this for decades, as has Alvaro. He's a Postgres committer and does his own brand of trainings and stuff. So anyway, I wanted everyone to know there's a URL on the top right of the screen where they can grab the calendar invite if anybody wants to join on Discord and listen in.
Thanks for that invitation, Claire.
Yeah, I don't know what you're going to say, but we'll find out when we get there. So Yalta, do we have questions for Boris? I know we have to move quickly to the next speaker.
With one question. You've done some support as well, right? How often do you see this wraparound problem? Is it super common, or is it sort of a rare one?
It is becoming a little bit. It is becoming more common recently because of the amount of data that people is putting on the databases and the amount of workload that is being. I mean, we saw it in the previous presentation about the amount of transactions per minute that you can add and all this kind of stuff. So yes, it is becoming a little bit more common. And there are two things that Postgres is trying to do. Either is to change the way that this 4 billion transactions is the limit. You have a larger spectrum. And the other things are a little bit more ambitious to have different type of storage system like the C heap and things like that. But until we get a proper solution for that, I think it's very important to just make sure that your auto vacuum is working properly. If your vacuum system is working nicely, you never have this problem. That's the main thing. Observe the visibility, observe for long-running transactions, and then you should be fine. I mean, if you're careful, this is not going to be hitting you anytime. Yeah.
Okay.
And then I just have to ask one more question. I know you have a PhD in computer science. I'm just curious, have you been working with Postgres since your grad school days, or is that something that happened later in life?
So I did some Postgres before I did the PhD with Alvaro, actually, in 2001. That was my first work with Postgres. But then I went to do the academia part, and I worked with actually peer-to-peer systems. So things very similar to Citus and MongoDB. But when I needed to compare some of the algorithms, I came back to Postgres to see how Postgres implemented two-phase commit, for instance. And then I was easy, although I don't program that much in C, but it was super easy to learn from the code itself. And then I said, wow, this project is super cool. I need to get back to do some Postgres stuff. This was, I think, 2008 or something like that. So, and then what I do is kind of mixing whatever I learned during my research in the PhD with whatever I do with Postgres now. So I try to do the merge and have a holistic view of the whole thing.
Bring those things together. Well, thank you very much. We'll see you on Path to Citus Con on May 3rd, Wednesday at 10 a.m. And you're going to go to the Discord, I'm sure, to answer questions and talk
Absolutely.
to the
I'm going to
other
stay
folks there.
hanging out in this Discord, not just today, but the rest of the week as well.
Okay. Awesome. Thank you, Boris. Thank you
Good.
so much. Okay. And I think without further ado, we should invite our next guests, right?
Yes. The next ones are Bob Wijsman and Eleni Ciampali. And they both work at Ubiquity. Bob is head of production, and Eleni is a data engineer. And you're both using Azure Database for Postgres Flexible Server, right?
Yes, we do. Yeah.
Okay. So I think you're the only customer talk in today's live stream lineup. So you're special. You were special anyway. But
Yeah, we feel really really honored to be in that spot. Yeah.
Awesome.
Thank you, Claire.
Yeah, welcome. Well, without further ado, let's get us started. Bob, you're going to take the lead, right?
Yes. Great. So I'm Bob Huisman. I'm the head of production of data and technology within Ubiquity, and I'm going through this talk with Eleni, who's our senior data engineer. And we were facing the problem of slow queries that were fast previously. And we did a lot of things on performance optimization. We had our indexes straight. We thought about foreign data wrappers, query plans, etc. And then we ran into the topic of bloat and auto-vacuuming. And it was very interesting for us because we have around 80 databases and around 7,500 tables, and these are growing. For the record, we are working on a Postgres single or Postgres Flex server 13.3, hosted on Azure. And yeah, we talk about the journey on how we will manage to set the auto-vacuums right for all those different tables. All right. So before we dive into a bit of the content, we want to first introduce a bit to Ubiquity, the challenges that we have faced, the impact of massive bloat, and then we go through the design and the implementation of it, and some important steps of database table segmentation. So Ubiquity is the world leader in media investment analysis. We work for the biggest advertisers of the world, including Johnson & Johnson, Mars, Volkswagen, Unilever, etc. We do not analyze advertisements on individual levels, but we analyze them on campaign level. That has some benefits, and also for our clients, of course. So over time, we have analyzed by now 5.5 trillion impressions. So that means that we have analyzed 5.5 trillion pairs of eyes watching an advertisement on any given website. Therefore, our client project dynamics made it pretty hard for us to set auto-vacuum settings right. Because as we all know, when a project starts, internal or external, it's very likely that the scope will change. And the further you're on the project, the harder it is to adapt, and the more it costs. So during the project, we see many delete updates and additional inserts to comply with the scope, adding a lot of bloat to any table. It can also be that when we are crunching the data and our media analysis is already started, we find some QA issues to deliver data or other issues in the ETL, and that also returns in deletes, updates, and additional inserts, more bloat. And then we get to the presentation stage of a project where we present our data analysis to the client. They want to know more, they got a better understanding of the data, and that can also result in more inserts, updates, and deletes on data in our tables. As you can see, we accumulate quite a lot of bloat in each client lifecycle. This is how it looks. If you visualize it, normally we would like to see a more sequential approach where we have the bullets next to each other. First you initiate your project, then you do the data crunching, and then followed by a media analysis. Unfortunately, they go hand in hand, and it's up to us to make sure that our processes are as fast as possible, and that we are agile enough to adjust to new client wishes. Meaning then an additional factor that makes it more complex for us to manage all those databases and all those tables is that we were not able to predict what the right auto-vacuum settings are at the start of a project, and therefore the auto-vacuum settings and the auto-vacuum analysis settings that are set by default by Postgres did only fit a small portion of the tables, as we found out. And monitoring and setting the settings right for 7,500 tables, it's not something that we want to do manually. It's basically impossible. So as you can see, we identified that there were 4 types of client project workload types. Some projects saw a big spike in the beginning and everything smoothed out during the rest of the year. Some had a very stable workload, some had a spike in the beginning, in the middle, in the end, and some just were very random. yeah, so we had to be able to adapt to it and make sure that our query performance was always on par with the needs of a project and our internal stakeholders like the analysts and the client engagement managers. The ineffective auto-vacuum settings accumulated massive bloat because the bloat was not vacuumed correctly, or a vacuum was not started at all, as we have found out for certain tables. The bottom line was the settings by default are not aggressively enough for the bigger table, or too aggressive actually for our smaller tables. We made sometimes a controversial move as we ran some vacuum fulls to remove the excessive bloat and return it to the storage of the server to make sure that tables are clean again, and the query performance actually really improved. And we consider this as the new clean state of a table that we want to maintain at all costs. And with the current versions of PostgreSQL, a vacuum full is not as dangerous as it was in the past. So here you see an example of how a massively bloated table looks like. And in the dark below, you see which actually data space is used by live tuples. And then after an insert, an update, and a delete, you get and deletes. You see a light blue bar on top. That's out vacuumed, and it's kept reserved for a table, which is fine because it makes it easier later on to run updates, insert, and deletes on that same table. However, we saw also a big portion of unvacuumed bloat taking a lot of disk space. So we needed to clean that up and make sure our server was clean and our tables were fast and the query performance was optimized. As said, we ran some vacuum fulls to clean and return excessive bloat. We tested before and after a vacuum full some basic queries that are executed a lot by our analysts, and they do basically a sum and count based upon the 3 most important dimensions that we have in our databases. And with the new table state, we would consider that as a good state, and that we want to make endure forever. So what were actually the structural performance improvements we made? You can see a good bullet chart of how it looks like. So we returned, by cleaning those tables, we returned 1.5 terabyte of disk space to the server, and that's equal to 30 client databases, which is quite a lot. It's worth for 9 months of new clients, so to say. And we saw 70% average query time performance improvement, which made our analysts very happy, of course. And it depends a bit on what kind of table, of course. And now I want to pass over the stage to Eleni to go through the design principles and how the actually implementation really worked. So Eleni, up to you.
Yeah, hello everyone. I'm Eleni, data engineer at Ubiquiti, and yeah, I will show you more about the technical side of our approach and how we manage to automate the whole process. So yeah, let's start. Thanks, Bob, for the introduction and the business impact that you showed. So I will discuss more about our design principles first. So what our design principles were for this approach. So the first part is that the solution should be run fully automated from end to end. That means that if we have any new client database or any table in the future, this should be automatically included in the solution. Another important aspect is that monitoring and alerts should be there in order to have an overview of the health and the correctness of our auto-vacuum settings, so that we know what the auto-vacuum settings are on each table at any time. And we wanted all the settings to be transparent to us. And the last one is that the categorization of the table should be dynamic, which means that any table should be able to move between segments at any time based on the current workload. And I will discuss about segmentation in a bit. But before that, let's go to a high-level design of the whole process. including some steps and some applications and tools that we used. So as you can see, we made use of different tools, and starting from the left, we collect different kind of metadata from all our client databases, and we store them into a central metadatabase tables. After that, we made a segmentation in order to determine the scale factors and the out-of-vacuum factors that we want. And as last steps, we store them into another table and update all the factors accordingly based on our segmentation. And this is our whole process and then end pipeline, which is managed by Airflow. So we use Airflow as tool, which is an open source tool which is used to orchestrate all our jobs. And the idea behind Airflow is that we have the whole process into a single DAG. And by DAG is the main concept actually of Airflow. And yeah, it includes different tasks which you can manage and orchestrate at any time. So in this drawing here, you can see how our DAG looks like, and you can see that we have different tasks of the process. I will go a bit into them. So some tasks run in parallel while others in sequence, but this is how the whole process looks like. The DAG runs every night, and the duration is 1 hour, more or less. And currently, based on the total number of tables that we have, it's around 236 tasks in total that run. So let's make it more clear and go more into the pipeline and the tasks. So first of all, every time that we start the process, we generate a unique ID, which enables us every night. It's good to have a unique ID of the process so that you can log and you can see what goes on there. So after we log the process, we loop through all our client database tables and we execute some analyze command there, SQL analyze command. And we do that in order to get the most updated table statistics. So after we execute the command, we extract the data that we want and we push all the data into a central table. At this point, after we have all the information, we create an access token because we want to connect Airflow with Databricks. And the idea is behind that is that in Databricks, we have the whole analysis of our tables, of some of the data we want, like the dead tuples or the live tuples of its table. So we do some analysis there and we do table segmentation. So create different segments and different categories for each table. After this step, we update, and having defined the out-of-vacuum settings that we want, we update all the factors and the settings accordingly to each table. And again, this is done with Airflow. Once more, I will go quickly through the steps just to make it more clear. Actually, this I will discuss about the main steps. So first thing that we do when we are on a database table, we execute analyze command to get the most updated table statistics. We extract the statistics. Some of the important features are the rel tuples, which is actually the number of rows, or the dead tuples. Then we push them in some tables that we have, central tables, aggregate information there is pushed. Next step is to create a connection between Airflow and Databricks, and this is done using service principal. And after we have the connection, we initiate a Databricks job from Airflow. And actually in this job there, the whole analysis is performed from end to end. And table segmentation is done and optimization of the factors is done. And then as last step, we extract the segments that we have been created based on the analysis, and we update all the out-of-vacuum factors accordingly on each table based on the segment that the table belongs to. So that's it for the pipeline. Next, I will tell you a bit more about the analysis and the formulas that we used. So this is a snapshot, a bar chart actually, of at a specific workload and how our data segments distribution look like. And you can see that we have defined 7 segments in total, and you can see different number of tables fall under each segment. And I will discuss first segment 1 to 6 and how the out-of-vacuum factors were defined there. So the segment categorization, it was done using a density ranking function, which is a Python function, and with some adjustable weights. So using this density function and the deviation of the rel tuples and the dead tuples, each table was assigned a score. And this score is defined in the formula below, and it's a custom formula that we defined, and we made use of the rel tuples and the dead tuples. And you can see here that we have 2 factors. So using those 2 factors, A and B, we can adjust them accordingly. And this is based on this score, we create the scale factor of our out-of-vacuum for each table. That's all for the more optimized way or the more optimized segments. But for segment 0, the first segment actually, we need to follow a different approach there because this segment includes only outliers, so tables that have very high volumes of data. So we needed to take care of them. So for that, we used a more aggressive formula, and we had to define the factors manually. But of course, this was again done after some investigation and analysis. So for this segment and the tables that fall under this segment, we set the scale factor to 0 and the out-of-vacuum threshold to 200,000. And yeah, you can see in the formula below how the threshold is defined using the total rows and making use of the factors and the threshold of out-of-vacuum. Yeah, that's it from my side. Bob, are you ready to wrap up?
I'm ready. Thanks, Eleni. A great explanation, I think, of the technical setup. It's quite a journey to get there. So to wrap it up, with this approach to have a dynamic table segmentation and adjust different out-of-vacuum settings to those tables, we made significant gains that are sustainable over time. We were able to save a good 1.5 terabyte of data, and which is equal to 30 client databases, which is quite a lot for us. The end-to-end automated pipeline makes that make sure that the settings are always optimized, and we don't need to make any manual adjustments now on it because it's runs every night, and when a new database is created, it's included there as well. When you copy this, when you also would like to work on this project, make sure that you are monitoring it closely as well, because different segments might require different formulas, as we have found out. And with the right alerts on the pipeline and wise monitoring tools on Airflow, we are able to spot any issue with the pipeline or any abbreviation of our normal durations. And of course, there are many other factors that can be taken in consideration for out-of-vacuuming. I think a lot of has been covered by previous speakers, like cost limits and workers. We haven't touched that in this project yet because we first wanted to review the solutions when this project was running for some time, and but it's definitely in the scope for the future. At some point, we were in a dead spot with a project, so we want to acknowledge some people, or one of the people of Microsoft Azure Database for PostgreSQL Server community. We want to thank Gayatri Paderla for her help and time to help us over that moment. and also Alicia Kucharczyk, who helped us with some examples and good materials to go through, and Sunil Arkawal, who pointed us to the right people and right resources for this project and also other projects. So thanks a lot for helping us. I hope you learned, everybody who was watching learned something from this talk as well, and how it can speed up your business. If you find yourself vacuuming your house afterwards, sorry for that, there's a lot of background talk going on today. And if you have any questions, please let us know on the Citus Con channel, and we're happy to respond.
Awesome. Thank you so much for joining us, taking time out of your regular workday to tell your story.
Our pleasure.
Our pleasure.
Yeah, it was a very interesting story. Well, one thing that I was wondering though, why are you running so many databases on one single server?
It's kind of a legacy reason, as we started a couple of years ago as a small startup and only needed one database server basically, but we grew exponentially fast. We're acquired by Ubiquity 2 years ago, and we are about to migrate in our current tenant to the Ubiquity tenant, and we thought it was easier to only switch one database server and then split the server up into smaller servers and then do it before the migration. So maybe next year there's a talk about how you migrate your server.
Well, I just wanted to remind everybody who watched your wonderful talk that I'm popping up a banner on the screen, that there is an attendee survey, and it's not just about the event, but it's about any of the talks that you might have watched. And I'm sure both of you would love feedback. So if people have a chance to go do that, I would really appreciate everyone in the audience doing that for the talks you've watched today. And Eleni, ευχαριστώ πάρα πολύ. Bob, thank you for joining us. And yeah, we'll see you on Discord.
Thank you. See you there.
Bye.
Ciao. Okay, it's time to invite our sixth speaker. We're running a bit behind, but it's a good thing we had a wrap-up session at the end. Alexander?
Hello, everyone. How are you doing?
Wonderful. So you are known as the main Patroni author. You work on that project. You now work at Microsoft, and Patroni is a pretty famous high availability solution for Postgres for anyone who's not familiar. And you're going to talk to us today about Patroni together with Citus, right?
Yeah, exactly.
Awesome. Well, let's let you dive in. Let's go.
All right. So Postgres is a wonderful database in all aspects. It's very fast, it's very flexible, it's extensible, but it comes unfortunately with batteries not included. What does it mean? If you want to have automatic failover with Postgres, you have to use some external tools. Or if you want to scale it out horizontally, you also need to use something external like Citus. And today I'm going to talk about how to make Postgres rock using Patroni and Citus together. And yeah, so what is this talk about? First, I will do a short and brief introduction to what kind of problems we are trying to solve. Then, naturally, we will speak about how to make Postgres highly available using Patroni, and how to scale Postgres horizontally using Citus. And as a next step, we will use all these three tools together to have the best solution. Of course, this presentation will include a live demo, and at the end, we will have a short wrap-up session. So let's try to scope our problem that we are trying to solve. Usually, when you're a business or application developer that works for a business, you want to have a database to use from the application. And database could be totally different in the real world. It could be even something embedded like a SQLite, which is also a wonderful database. But if you want to have a database highly available, it must be connectable from many different sources, from different components of the application, and you need to run a primary and a standby. And in case of primary fails, you want to have it failing over to a standby. The next thing that people naturally want, when business grows, you want to be able to scale out or scale up, depending on the business needs. And scaling means two different things. It could be scaling up vertically, like you want to throw more hardware you want to buy a bigger machine and scale out vertically, or better, you want to scale out horizontally. That opens totally new perspectives. And last but not least, we want to do it for free. Like, of course, you can buy a ready solution from any of the cloud providers that will allow you to scale Postgres even horizontally. But it's not always possible to run your business on the cloud. Sometimes there are strict requirements and you have to stick with on-premise. You have to stick with the real hardware. And therefore, we want to have something that is available and better for free, because the best beer is the beer you get for free. All right, so with choosing a database, it's very simple. First of all, we are a Postgres conference, and using a Postgres is out of the question. And this picture I took from Postgres website, as well as a quote that the Postgres is the world's most advanced open source relational database. So we will use Postgres. And to make Postgres highly available, we will use Patroni. So if you're not familiar with Patroni, it's a daemon implemented in Python. It runs next to a Postgres processes, and in order to figure out which node should be running as a primary, Patroni relies on a distributed key value store, such as etcd, Consul, or Zookeeper. And those are probably three most widely used and most well-known distributed key value stores. To provide a single endpoint and for the applications which will connect you always to the primary, we typically recommend using a tool like HA proxy or any kind of TCP load balancer that may choose the node which is running the primary by running a health check, REST API health check provided by Patroni. Basically, HA proxy simply calls HTTP endpoint on the Patroni on every node, and Patroni responds with HTTP status code 200 when node is running the primary. And in case of it's a standby, it will respond with code 503. Actually, HA proxy could be also used for a different purpose. Like it could be doing a different health check and exposing a different port to do load balancing across multiple standbys. So how to scale Postgres vertically? Well, how to scale Postgres? Like the first one, which is very obvious and available for anyone, you just throw more hardware. You buy a bigger virtual machine, or you buy a better server, and you set it up. You, as a standby, you do a switchover. So the node which is currently as a standby will be a new primary, and the old primary could be decommissioned and also rebuilt on the bigger hardware. But as we know, and as Marco noticed in his keynote, ability to scale vertically is not infinite. At some moment, you reach the biggest possible machine that you can buy, and you are locked. And resolving the situation, it could be very tough. Therefore, people, when they have in mind solving of scalability problems, consider doing sharding from the early stages. How does it work? Instead of running just a single Postgres instance or single Postgres cluster, we run multiple Postgres clusters, and our data will be spread across those machines, across those clusters. The way how you spread the data across different machines or shards could be as simple as we divide some identifier, which is used as a sharding key, and take the reminder of this division. And in case if we have only 4 shards, we can take a remainder of when dividing by 4, and the remainder will define the shard ID. It's very simplified. The real solutions, of course, not using this approach, or maybe they do use this approach, but with application level sharding, there are definitely pros and cons. The main advantage of application level sharding is that application connects directly to every shard, and latency is very minimal. So it does not see difference comparing when it works with just normal Postgres, because it is a really normal Postgres without any hacks. But there are at the same time plenty of disadvantages when you use application level sharding. On the application side, you have to know to which database, to which shard you have to send query to, and therefore you need to have a dedicated connection to this machine. When you build your database, or when you build your application, you have to think about sharding from the day one, and you have to think about data locality. It means that for a given customer, you have to store all orders that this customer makes on the same machine, on the same shard, in order to perform joins effectively. And actually, with application level sharding, I would say it's very close to impossible to do cross-shard joins. It's also very tough to add new shards, especially in case if you shard by a reminder of your sharding key. And but at the same time, you may invent something better and shard by using different strategies. So adding new shards will be possible, but when you add new shards, they will be heavily disbalanced. They will have no data and they will receive no queries. And only after significant amount of time, they will get some new data, and maybe somehow system will become balanced. Enterprise solution should support rebalancing of existing data between old and new shards, and preferably without downtime. And it's actually a huge challenge. And last but not least, when you develop your application, when it evolves, you also have to do some changes in the database. And since you have not just a single database, but the whole bunch of them, all changes must be deployed to all shards. And in case if you fail doing so, application may start behaving unexpectedly. And Citus is a solution to Postgres horizontal scalability. Instead of doing all this stuff in the application side, Citus provides a single endpoint where you can do everything to shard your data. In the Citus, there are two concepts. There is a Citus coordinator, which normally is used for application to work with the data, and also what is important, your application will use a coordinator to change schema, to create new tables, to make them distributed. You may also, of course, insert data into those distributed tables, and under the hood, coordinator will parse those queries, rewrite them, and send them to a set of workers, which are known also as shards. With Citus, of course, there are plenty of advantages, but one disadvantage is because we have to parse the query, we have to do additional catalog access, Postgres catalog access. We have to construct new queries and send them to worker nodes. at the end, we get some additional latency, which is a performance killer, as also Marco noticed. But I believe there are plenty of advantages from Citus. It's transparent for the application. So not totally transparent, because when you design your database schema, you still have to think about data locality, and you have to put some collocated data. So you have to design schema in a way that collocated data will be placed on the same shard, on the same working node. But from the application, you connect to coordinator, and therefore there is not so much changes comparing when you connect to just a single Postgres. It's a single connection pool, but at the same time, Citus provides the ability to connect to any of the worker node and also run any query, and it will work the same way as it works with coordinator. Although you cannot deploy currently schema changes via the worker nodes. And what's the biggest advantage of Citus? You can start with small. You can set up originally just a couple of worker nodes, and when your business grows, when the amount of data grows, you can add some additional worker nodes and scale out. And what's more important, if you did your homework good, so if you created schema in a way that it could be, it has all primary keys or has some unique keys, that it could be rebalanced without downtime using logical replication, which is again available on Citus for free right now. How we can combine those two solutions together? How we can make Postgres highly available and scalable at the same time? Of course, we can again deploy multiple Postgres clusters with Citus extension, one coordinator and a bunch of worker clusters. And under the hood, Patroni, using the distributed key value store like etcd, Patroni on the Citus coordinator can discover all existing Citus workers that also registered in etcd, and it will automatically register every new worker which is added on the coordinator. What's also interesting, when the roles of nodes in the workers are changing, when standby, for example, becomes primary because the old primary failed or because we did a switchover, the Patroni on the coordinator will update Citus metadata to reflect those changes automatically. You don't have to do anything special for that. And application will, as I said, will just connect to the coordinator, or in case if there is a demand, there may be a special HA proxy running just for accessing worker nodes and doing load balancing across workers to send queries to. How to enable Citus support in Patroni? It's fairly simple. There are just a couple of simple rules that one needs to follow. If you're already using Patroni, you're familiar with Patroni config file. If you are not, it's actually pretty simple. The scope or cluster name must be the same for all clusters of our Citus cluster deployment. Like from perspective of Postgres, coordinator and worker are different Postgres clusters because they will have different system identifier. But from perspective of Patroni, we need to combine them logically together, and therefore we have to define the scope as the same on all nodes. At the same time, the group ID must be different for coordinator and for workers. For coordinator, the group ID must be 0 because it is how it's defined inside Citus extension. And for worker nodes, the group ID must be just unique and the integer, like 1, 2, 3, and so on. And last but not least, we need to specify in which database we want to have our data, where we want to create our Citus extension. And in this example, it's a database named Citus. How to solve problem of scaling out when we add in the new workers? It's also very simple. We just create a new Patroni YAML file, Patroni config file, and there are a couple of parameters that needs to be adjusted. Of course, it's a unique name of this node, the Citus group, which also must be new, and it should not be the same as on existing nodes. And we just start Patroni with a new configuration file. Basically, that's it. But after that, this node starts completely empty, and we need to move some existing data to this node. And for that, Citus provide a user-defined function, UDF. It's called Citus rebalance start. Starting from Citus 11.2, it's possible to rebalance data without keeping client connections open. Basically, you start this job and you can leave. At the same time, if you are interested about the progress, you can use the other UDF called Citus rebalance status to check the progress. So, all right, I believe it's enough theory for now, and let's do a live demo. Let's see how it works in practice. To do a live demo, I'm going to use Docker Compose and Docker to start a bunch of containers. I already deployed it, and we got a bunch of containers running. But while they are starting up and cluster is being formed, let's look at Docker Compose configuration. In the configuration, we have a etcd cluster, which consists of 3 containers, and 3 it's a minimal number for etcd to become highly available. It means that every node of etcd could be lost, and while there are 2 remaining nodes that keep running, it will be still running and response on any kind of queries, reads or writes. We also have in the manifest HVA proxy container, which provides a single endpoint and can connect us to either to coordinator or to worker nodes. We have 2 containers with coordinators that also create a highly available cluster for Citus coordinator nodes, and 2 pairs of containers with workers. Okay, so we can go inside a container and check the status of our Patroni Citus cluster, and it's up and running. We got 3 leaders, 1 for coordinator and 2 leaders for worker clusters. And here we see, like if you are familiar, if you are existing Patroni user, you will see something not familiar. So it's a quorum standby. Basically, at the same time, it's a version of Patroni which is not yet even in the master branch, and it shows that quorum commit feature is working. Let's connect to our database, to the coordinator. It is accessible via HA proxy on port 5000. And we can check PGDist node table, which contains Citus metadata and contains all nodes of our Citus cluster. And we see that coordinator primary and 2 standby, 2 worker leaders primaries are registered in PGDist node. We can also check extensions that are created in the Citus database, and we see a Citus extension, but it was obvious, otherwise we will not see PGDist node table. What else I'm gonna do? I will add some test data, and I'm using for that example from Citus documentation, because otherwise doing rebalancing will be very boring. And the last thing that I'm gonna do, I will create yet another table, make it distributed, and start inserting data into this table with like interval every 100 milliseconds. While inserts are running, let's add some new nodes to our Citus cluster, but to the group 3. We again deploy our Docker Compose. Existing containers are up to date, but 2 new containers are started. And again, go to the HA proxy container and check patronic control list. And voila, so the third node already is added to the Citus cluster, the third worker. But while it's being set up, let's do a switchover on one of the worker clusters. Let it be cluster from group 1. But the patronic control tool switchovers adjust the current running primary on this cluster. It also asking to which node you want to do a switch. You can either specify a node or you can leave it empty. And when you want to do a switchover, you can do it either now or you can specify any arbitrary time in the future. So it will be done at let's say deep at night when everybody is sleeping and not so much traffic. And we will do it now. And the last confirmation and switchover starts. All right. As you see, the query latency was around about 10 milliseconds, the insert latency. But during the switch, it jumped just to 3 seconds. It could be sometimes a bit more than 3 seconds. It could be a bit less, but this is how switchover manifests itself. And it's possible thanks to Citus' ability to pause client connections to the coordinator. Of course, unfortunately, if you are sending queries directly to worker nodes, it will not work so flawlessly. But this is still a nice feature that works right now. If we check patronic control list, once again, we will see that switchover completed and worker in the group 1 already is on timeline 2, and everything seems to be nice. And our queries are still running. So the next thing that we're gonna do, we will check Citus shards table. We want to see how our data is distributed across worker nodes. And because when we inserted this data, we had only 2 workers, and therefore we see only 2 nodes which hosts the real data, except one table, which is geo IPs, and this table is not distributed but a reference table, and therefore it's also hosted on the coordinator. After adding a new worker node, we want to rebalance existing data. And for that, we will use Citus rebalance start UDF. And we also can check the progress of rebalancing. And it's quite a neat feature. And at the same time, we will see on the left side on the screen that transactions are still running while data is being moved between different workers. It does not really affect existing transactions because under the hood, Citus uses logical replication. And instead of blocking writes to the shard table, it just takes a very short lock when it needs to do a final switch. Right now, out of 11 tasks, 7 already done. We can check again Citus shards table to see that the new node got some data and it indeed some data moved to the new node, which is pretty neat. And we also have it for free, as I said. And while we were talking, the finally rebalance finished, and we are good. So basically, just in a few minutes, we not only deployed a new shard, but we also successfully scaled it out. And now it was it for the demo. Can we get back to the presentation? Yeah, thank you. And it's time to wrap it up. With Citus and Patroni, we can have an enterprise-ready solution that allows that makes Postgres not only highly available but also scalable horizontally. You can start with very small scale, just with a couple of worker nodes, and scale out later when there is a demand. In case if there is no demand, actually you can even scale in, which requires a bit more manual work than scaling out, but it still works. And what's also wonderful that everything is open source. Postgres has a very good license that allows you even to fork or maybe even sell if you want Postgres. Citus is also an open source extension, maybe not with such good permissions as Postgres itself, but still it's open source, and Patroni also an open source tool. And you can get Patroni and Citus on the GitHub. You can install them and use it for free. And that was it for my presentation. Thank you for listening. I hope you enjoyed, and now I'm ready to answer all questions.
Awesome. That was really, really good, Alexander. Thank you. And a demo. It's always good to see something in action. And yeah, and you didn't have a backup demo recorded either, and you knew it was just going to work, which is great.
Yeah, so sometimes I script my demo so that I don't have to type anything, but it looks also boring because you know, so it's already scripted and nothing can go wrong. But sometimes when you screw it up or you can do some little variations, it's also nice, in my opinion.
And so I guess most Kubernetes fans will be at KubeCon. That's also being held now. But I think in like you showed Docker Compose, is there also any Kubernetes integration?
Well, yeah. So Patroni like natively integrates with Kubernetes. It makes Postgres Kubernetes native, I would say, and it started doing it before it became a mainstream, as some other companies saying right now. Basically, Patroni works on Kubernetes starting from 2017, and now you can also deploy Postgres with Citus on Kubernetes, and it will work the same way as I did currently with Docker Compose. Basically, everything is declarative. But to get the best, you probably need to wait until some Postgres operator will get some Citus integration. But at the end, it will be handled by Patroni. So all these features that I showed will work the same way.
That sounds very cool.
I know there's another talk. It's an on-demand talk at Citus Con, an event for Postgres, called Citus on Kubernetes. And it's about, isn't it about the new operator from Stackgress?
It's
I think so, yeah.
Not totally new, but it's existing operator, but they are working on adding Citus support, and they have quite a good progress.
Yeah. I was reviewing the captions for Elvato's talk before it went live, so it published yesterday.
Great. I would recommend all Kubernetes fans watching it.
Yalta, or other questions that we definitely wanted to answer? I think we have time for one more.
So let me take a quick look. So yeah, what future improvements have you planned for Patroni? Like you added Citus support recently, so what's sort of the next big thing?
Oh yeah, so that's a great question. The one very major thing, it was like partially revealed in this demo. It's a quorum commit feature, so that Patroni can not just stick to a single standby as a synchronous, but it will add all the existing standbys that are eligible to be synchronous ones. And when failover happens, it needs to query all of them to get the quorum number of votes to be promoted, something like this. And it will decrease latency when synchronous commit is enabled, and of course it will also improve availability. So it's going to be a great feature.
That sounds amazing.
So for
And
those
it will work with Citus too, right?
Yeah, for sure. And as I showed in the demo, it
Yes.
does work with Citus.
For those of you watching, Alexander is probably going to hop over to the Discord. And are you going to be publishing your slides from the talk?
Yeah, for sure,
Okay.
for sure, yes.
And I know that all
I
six.
will put them to speaker deck.
Okay, awesome. And all 6 of the live stream talks today are available for replay. We'll post that link in the Discord as well, or actually I have it right here. Watch the replay of the Americas Livestream and the EMEA Livestream. This is a playlist of both live streams that I'm showing in the bottom of the screen. So if you missed part of Alexander's talk, or you want to go watch his demo again before we publish it as a standalone video, you can go do that right now. So thank you very much for being part of Citus Con this year, Alexander.
Yeah,
And
welcome, and see you on Discord.
see you on Discord, and hopefully I'll see you at the next PGConf EU in person again. We'll see.
Yeah, for sure.
Okay. Ciao, ciao. So I think next we move on to do our wrap-up session.
Yeah, we do.
We're running a little bit late. We were supposed to end at the 30-minute mark. That's 10 minutes from now. So our producer has graciously agreed to allow us to run 5 or 10 minutes late. So for those of you in the audience, we just want to share some information and reminders that are useful. And there's some videos that we want to roll too that give you a sneak peek, an even better sneak peek into those on-demand videos. So let's see, what do we have here? Oh, the reminder about the survey. If you've ever given a talk, you know how valuable that feedback is on your talk. So please, as a gift to the speakers and the organizers for this virtual event, like we would love your feedback. Survey's open till next Friday, the 28th, end of day, anywhere on Earth, 11:59 p.m. PST. And then Yalta, what are we going to say about the Discord?
I mean, go there, ask questions, talk to people, or just read what other people write. I mean, you can lurk as much as you want. It's fine as well.
Lurking is okay. All right. These are the talks that we just reviewed, and I just popped the live stream playlist URL on the screen again, so you can go watch them or screenshot them or send them to colleagues even before we publish. And then I just wanted to remind everybody that Boris, who did the storytelling, is, along with Alvaro Herrera, going to be guests on Path to Citus Con on Wednesday, May 3rd. It's a really cool format. We kind of stole the idea from Brian Cantrell and Adam Leventhal and folks at Oxide Computer, who have been doing these live shows on Discord where there's a voice conversation that ends up getting turned into a podcast recording, but then in parallel, there's this live text chat. So everybody in the audience kind of has a chance to participate, drop in links, add comments, and it's so you're interacting and experiencing the event on 2 levels at once. And it's just a ton of fun. So our first 2 episodes were pretty popular. We're going to do it again. And this one will be about why giving talks at Postgres conferences matters, which seems appropriate for me to have mentioned here. So was that too much of a sales pitch? I'm just so excited about this.
No, it's fine, Claire. It's a bit of a sales pitch, but it's okay.
Okay. All right. We already mentioned the Americas Livestream that you can watch. Should we roll some of these on demand?
Yes, let's do it.
Okay. So let's roll the first one on Postgres performance and security.
But in fact, I'm going to show you different, hopefully exciting ways that you don't know about to index UUIDs in PostgreSQL.
So if you are a traveling Postgres consultant like me, so we see that often a lot of performance can be gained by outsmarting people, right?
Today I'm going to be talking about Postgres table bloat, but the overall idea of this talk is discussing the transition from doing Postgres at a smaller scale to Postgres at scale.
I'm going to talk to you today about PostgreSQL privileges, roles, and security, and how you can take better advantage of them within your Postgres installation.
The thing I wanted to talk about, explain the concepts behind tuning high-write workloads for Postgres, and then dive deeper into the specific configurations.
I'm DevOps Data Technical Lead of JFrog, and I want to share my lecture about troubleshooting high CPU utilization for Postgres database.
We'll talk about external attacks, about authentication security, about data protection, and also I will share some tips and my recommendations with you.
Yeah, no, this sounds amazing. I'm a huge security nerd myself, so I'm definitely going to watch Taras' his talk.
Yeah, I think we could spend 5 minutes talking about each one of these. And the thing for me that's so cool about being involved in Postgres conferences is this is how I've met some of these people, right? They don't work with me on the Citus team or at Microsoft. Well, other than Samai on this grouping, these are all people I've met at conferences. And the Postgres community it's open and it's global and it's pretty fun. All right, so I think I have more slides here that we're supposed to go through. So let's see if I can click into them. I did want to say thank you to the talk selection team for reviewing all those proposals. Oh, no, I'm not trying to thank myself. No, that's not the point. But, you know, Alicia, Aaron, Charles, Marco, this took a lot of time. It was a big lift. There were a lot of submissions, and I really wanted to just give them a shout out.
Thanks to everyone. Yes.
And then here, swag. The code is on the screen, swag bag. The URL is on the screen. If you're here and you haven't had a chance to go do that, this activity book is actually kind of cool. Like I have it here. And I don't know, it's fun for kids. And it's fun for adults. And stickers. I just want people to be able to benefit from this. So I wanted to mention it. So because I'm not sure if the cutoff, I don't think it's like this minute. I don't think it's the moment the live stream ends, although it could be. So do it now. But it's certainly going to be today, like probably within the hour or something, but maybe before this live stream ends. So what else do we have here, Yelta, that we wanted to cover? I think the sticker packs too. That is a different code. So stickers. So if you want to enter for both, you got to enter twice using the same URL, the different codes.
You're allowed to. That's fine. You can enter to both of them. Totally acceptable. You don't have to, but you are allowed to.
Okay, it's good that you're giving people permission, Yelta, because you know they might not have been sure, and now they are. All right, let's roll the next video that gives some sneak previews of some of these on-demand talks. These are our talks all about Postgres on Azure.
Hey, Lucas here, and I'll present to you how I auto-scaled a Cosmos DB for Postgres cluster using Citus, of course, Grafana, and Azure Serverless.
This talk is for multi-tenant SaaS companies who are growing fast. That is, they're onboarding thousands of customers, and they are expecting or already running into scalability issues with their database and want to scale out with distributed PostgreSQL.
So today we are going to talk about multi-tenant software as a service applications on Azure Cosmos DB for PostgreSQL.
It's built upon like the community version of Postgres, so the open source Postgres, and adds also Citus extension, which turns Postgres into a distributed database.
In this session, I would like to talk about partitioning in PostgreSQL and how it is similar and different than Oracle.
So today's focus of the talk is to discuss some tools, recommendations, and best practices of how to reduce cost on Azure database for Postgres flexible server.
My talk is about Azure AD authentication with flexible servers. If you use flexible servers or plan to try it out, this feature will help make your application connections more secure. It will save your time managing credentials and roles, so please check it out.
Okay, so those are all good talks. I think I've seen all of them so far except for Addy's. Addy's the one who gives the Oracle to Postgres partitioning strategies talk. But I have to say, any talk that features Grafana in a demo, I'm always a fan.
Yeah, I used Grafana a lot at my previous company. It's amazing software.
Yeah, so thank you, Lucas, for putting that together for us. Let's see. Oh, I promised somebody I would put this slide up here. Speaking of Azure Cosmos DB for Postgres, which I call Citus on Azure because I work on Citus open source, but the service name on Azure is Azure Cosmos DB for Postgres. We had a big launch around that last October, and this training module was created by well, one of my teammates contributed to it, Joe Nelson, and it's supposed to be pretty good for anybody who's trying to get started. So I promised I would drop this up there with that short URL, although it's kind of a long URL. But anyway, that aka.ms URL for anybody who's looking to get started using Citus on Azure. So there, job done. We have another trailer. This one is from people who are either Citus open source users or in the ecosystem, in Alvado's case, or Onder, obviously you work very closely with him. So he's
yes, one of our colleagues.
Second from the right. Okay, so let's roll this one.
So this talk, we're gonna discuss a little bit why you want to run a database on Kubernetes, how this was done to run Citus, to create Citus clusters before Patroni 3.0 appeared, and the most important thing, how you can run Kubernetes, Citus on Kubernetes today with open source software in a very, very easy manner.
In my opinion, cybersecurity applications have a certain unique set of features and requirements that are different from other applications. I also think that Citus database is very uniquely positioned to solve many of the challenges that cybersecurity applications present.
I'm a principal engineer working on a platform here at Jellyfish. Been here since the early days and through a lot of our growth and our infra choices, including the move to a sharded database that we're going to talk with you here today about.
The purpose of this talk is to help get ahead of some of the gotchas that come up when trying to move to a self-hosted Citus implementation. We went through this journey, and we'd like to share some of the interesting technical challenges that we had to solve.
Because I frequently get questions about foreign key support in Citus. In this talk, I want to clarify some of the concepts regarding Citus.
Hello, I'm here today to share with you some lessons and observations from Safety Culture's migration from a managed PostgreSQL service to our own self-hosted Postgres.
Wow. Yeah, it's always great to hear stories from people using Citus and even the problems they run into. That, I mean, they're not so nice to hear, but they're good to hear, so we know what to change.
I'm trying to find the banner that I have that goes to all these on-demand talks. Oh, here we go. So if you want to watch any of the on-demand talks that we're showing, you can get to there from the schedule page. And this URL takes you to the schedule page with the on-demand tab opened. And there's YouTube embeds there for every single one of these talks. So I don't know. I do a lot of my learning on the weekends. I tend to sleep in on Saturday mornings and then, go for a hike with my husband and then try to read a blog or watch a video or something. So there's plenty to keep me busy and hopefully everybody else moving forward, but definitely go check those out. I think we have one more video to roll in a minute, but first this is just the Citus GitHub repo screenshot that I put up there. Seemed relevant to the talks that we just looked at. And I know you spend a lot of time here, Yelta, because you're pretty active.
I push lots of commits, review lots of PRs. So I know this page very well.
Okay. Well, yeah, that's where you live and work. Okay. So the next collection of mini previews of the on-demand talks, these are all Postgres ecosystem talks, Postgres community talks. Yeah, let's see what it is.
I am Dimitri Fontaine.
and I've been contributing to PostgreSQL for a very long time now. We're going to talk about how to copy a Postgres database, so from one server to the other one.
The concept of storing time with databases had been popular for a very long time, pretty much since relational databases come to life.
And secondly, the goal of this talk is to talk about how Postgres can give you an ideal platform to use artificial intelligence in your applications.
We'll set the scene by imagining that you're the DBA in an organization that needs to implement multi-tenancy.
What I'm going to talk about today is how we've taken PostgreSQL, a nice, sane relational database, and how we've twisted it and molded it and created what we think is a very robust document database and event store solution.
Today, I will talk about in-depth guide to the Postgres new CI, and I will explain how to use that new CI.
In this talk, we see together how to build web maps from scratch using Django and PostGIS. If you are asking yourself what type of maps we can build with Django, let's see an example right away.
Wow.
Yes, they all sound very interesting too. It's I'm definitely the whole playlist is on my to watch list in my in the time I have after this.
Jelte, this is actually the second time I've co-hosted something with you, right? We did a release party.
Yeah, that was also, I don't know, last December
11.2? 11.2?
I think it was around December.
Yeah, are we allowed?
It was also very fun.
Are we allowed to say anything about Citus 11.3? It's happening at some point.
I mean, it's very close. It's very close to. I mean, we sort of all have all the code pretty much ready. We basically, I mean, Citus Con was a bit like, we need to focus our efforts here for a bit, and so the next thing to focus our efforts on is actually doing the final release of 11.3. So it should be out in like a few weeks, like 2-ish.
So anybody who's on the Discord, obviously Rob Treat was the co-host for the Americas Livestream earlier today, depending on your perspective on time, and he's awesome, and that was so much fun. But those of you who are on the Discord right now who are watching, by all means, let us know if Jelte and I should co-host something else together in the future, like perhaps maybe the next live stream, or not the next live stream, the next release party. So let us know. And Jelte, we're going to be in trouble if nobody says anything. What does that mean? What are we going to do? Before we end, I wanted to throw the swag bag and stickers codes up there with the URL. If you haven't yet gone to request those, it'll get shipped to you. Your addresses will be treated very confidentially and, thrown away afterwards. So, and again, there's that invitation to join us on the back channel on Discord. Even though this live stream is ending, our speakers are still going to be there later today and probably tomorrow. And obviously there'll be speakers popping in who are on-demand speakers as well. So feel free to drop your questions there. It's very asynchronous, and that's cool. But hopefully they will see it, and when they get there, they will get you a reply. Jelte, is there anything else that you want to talk about in terms of like closing remarks? I put the survey URL on the screen because I think that's really important, and it's a gift, that you can give. So we're happy to give the gift stickers and socks and things, but we would love your feedback.
I think we're basically done, and I wanted to thank everyone that watched, because I mean that's what we're doing this conference for people to watch it. So hopefully you enjoyed it, and see you next year.
Long live Postgres, the world's most advanced open source relational database. Awesome.